Okay. Yeah. So hello everyone. Welcome to the Faculty Development Program Day 2 on VLSI System Design. VLSI Design using eSim and Open PDKs. So the first session will be taken by the FOSSI managers, and they will be briefing about the whole project and how it all started and what all we are doing. So over to you, Vinita ma'am.
Hi, good morning, all. So, really nice to see everyone coming on day two, early morning. Yesterday also was a good day. You got a chance to interact with Professor Kannan. So, I'll take a minute to introduce myself. I'm Vinita Parmar. I'm working with the FOSSI project since 2014, and earlier I was working with Professor Kannan in Spoken Tutorial Initiative since 2011. So, it's been a long journey with open source software. I've done my bachelor's of engineering in electronics telecommunication and my master's in electronics, purely electronics. Um, yeah, that's for about me. And let's get started about why we are here. So I'm going to give you a brief about what FOSSI is and what all you can do, how institution will improve, and lots of things are there for you. So I'll just share my screen and if you have any questions, you can just ask me on chat. Maybe at the end, we can have 2-3 minutes to discuss it. Okay. So I'll just share my screen and I'll have a small presentation to show you all. Is my screen visible?
Yes, ma'am.
Yes, ma'am.
Uh, yeah. So, like I said, I'm here to tell you about FOSSI. So, FOSSI basically is a government project and we are as everyone knows it stands for free and open source software in education. So already one e was there, so we could not remove that e, so that's why double e. So FOSSI stands for education in open source software. So what we are focusing is not on normal academic curriculum or anything. We are focusing on skill development where we build a bridge between the academia and industry, and how we do that through open source software that I'm going to tell you. And government has given, the Ministry of Education has given FOSSI the responsibility to make India aware, especially our academic people, academics, research people, and everyone involved in academia aware about the use of open source technology, so that it can be beneficial to the whole country later on. Okay, because education is base of every growth and success of and a development of a country. So that's where open source technology will help you build your success. So let me get started. So our basically, FOSSI aligns with the national vision, which is first one. I'll tell that these are two pillars. So, Atmanirbhar Bharat, because if you are using open source software, you are totally self dependent. You're not dependent on any proprietary software for doing any modeling
Ma'am,
or using
changing
any
the slides.
tools. Sorry?
Are you changing the slides?
Yes, I've changed my slides.
Your screen is stuck.
Okay, I'll reshare it again. Give me one minute.
Now it's visible. Yeah.
Now it's visible.
Yeah.
Okay, can you see the next slide?
Yeah. We are able to see it.
Yeah. So the pillar one, as I was telling, is Atmanirbhar Bharat. FOSSI aligns with the national vision. So using open source software definitely gives does not give any restriction on modeling or any licensing fees. You have complete freedom of firstly using it free of cost, and secondly, it makes you self dependent. Whenever you want to explore anything, you just install it on your system, customize it according to your needs, and you're good to go. So it will save your money as well, which you can use for empowering the institution, or using it for the infrastructure development. When if money is saved, we can use it in lot better way and empower it. So that is Atmanirbhar Bharat, where FOSSI is also aligning with those thoughts. And pillar two is NEP 2020 pedagogy, where the government is now focusing on multidisciplinary, where it encourages people to from different fields to contribute to different areas, to explore their skills in different areas. So like Professor Kannan yesterday told that he's a chemical engineer, but he is into he was our torchbearer for eSim, for open form, etc. So he is also involved in multidisciplinary fields. So that's why we do not believe, FOSSI does not believe that if you are a computer engineer or electrical engineer, you should do this only. You can explore your skills using different softwares, open source software. And like Maheshwari ma'am also said yesterday, that she was a computer, she is in fact a computer engineer, and she was teaching in CSE department, but then she was exploring eSIM. So like that, FOSSI has different examples where we do not focus on one field particularly. So we give benefit, or I would say opportunities to explore different disciplines and explore different skills in a student or any individual. Okay, so we also have tech integrations, like we have developed our in-house softwares, like eSIM is there, OSDAC is there. Also, our interns are contributing in developing this furthermore. So it's kind of tech integration for all of us, and all these gives us digital infrastructure. So we are not stuck to a smaller thing. We have developed cloud-based versions of different softwares also. So it basically gives a virtual environment and simulation labs online for us, which will give a digital infrastructure.
Listen,
For eSIM also, we are developing it.
listen.
Hello,
Slide is not changing like this.
hello.
Hello?
नहीं चेंज अब भी किया मैंने.
It's not changing. नहीं हो रहा है.
No, I didn't change it.
Okay.
I didn't change it.
Okay, okay.
Okay. So now I have changed. Is it seen?
No.
It's still stuck in aligning with the vision, national vision.
Okay. I think it will load. So I will share my slides with everyone if you guys can see it later. I will just reload it. Is it seen now?
Yeah,
Which slide can you see, Sumanta?
the FOSSI paradigm.
Hello. Yes.
Transforming consumers into
Okay. Yes. So consumer here actually means users who are using open source software, and who are actually using our FOSSI supported software. So earlier I will say the passive approach is where the people are dependent on software licenses. You have to pay heavy fees. There is restricted limitations. You cannot do more stuff. You can use it for some particular time, and in an institution there are limited license available, so it does not make it available for all the students. There are some computers which will have the license, some might not have. So it is not that user friendly, I will say. But whereas open source software, and where FOSSI stands, we empower students and faculty to build open source communities where they can explore, they can contribute to open source community, develop the open source tools. We handhold them. So where that is where their skills are upgraded. We handhold all our contributors who contribute to our activities, to our internship hackathons, to our workshops. So we handhold them, tell them, ask them to contribute to some particular we actually take them to a particular level by teaching them the open source software, and wherever they have a problem we handle them and tell them that this is the way you can approach, and then the profile is builded, the whatever the work done by any individual student, say faculty members or an institution, all is published on FOSSEE's website with their name and the report and the work which they have done. So that actually gives advantages to the students to get employment easily, because there is a direct link where the employer can see their work, verify it, and that too on a government recognized website. Okay, so I'll change my slide again. So we have a software ecosystem where for
Still not good.
numerical computation we have MATLAB. Uh, Mat. Okay, I'll do this.
This is better.
Always I'll do this. Okay, yeah.
Yeah.
So MATLAB, we have Scilab, or Python is there for where all engineering colleges can be used. For chemical engineers, we have Aspen. For eSim, definitely electronics people, ORCAD is the proprietary software. ANSYS Fluent, we have OpenFOAM. OSDAC is for steel structure design. For SPSS, statistical analysis, we have R. So and so on. There are many things which we promote, which you can see on the website. I will take a walk through the website also. So first thing our institution can do here with FOSSEE is you can actually migrate your lab, which will help you unlock the unlimited software access, which I was talking about earlier, to always available open source software lab, where you have to give zero license, where you can the students can explore limitlessly, they can code on their local machines. In fact, they can take the software on their system, they can do explore it at their home or remote places. Even at the institutional setup there will be unlimited access to these software. So we have migrated 1,000 plus labs successfully in eSIM, DWSIM, OpenFOAM, etc., etc. So we believe that the open source initiative starts from the classroom itself, and it will survive further if it is distributed through classroom, because that's where the students learn the new capabilities. Okay, so our next is what is our strategy to attain this. The first is you have to choose your software. Okay, then we have an activity called textbook companion. So this is actually a direct translation of a student takes a textbook, say for example a Scilab, for they have chosen Scilab. Okay, so they will code the solved examples of a textbook in Scilab. So the theory of the examples, the explanation of the example is already there in the textbook, but only the solved example code, the same result they have to replicate in the particular software. In this example which I'm explaining is Scilab. So step by step validation is done for these codes, and then there is a repository of the Scilab codes available for a standard textbook which is used in your college. So like that we have more than I'll tell in my talk, we have more than 1 lakh codes which are already published by these students across. So then definitely comes the lab migration. Once you choose the software, you have the codes with you through textbook companion, then you can do lab migration, where you have unlimited access to a license free software, where you can do all your lab examples in open source software. Then your students can actually, once they know the software and the software is available in the lab, they can actually contribute to niche activities like circuit simulation in case of eSIM, flow sheeting in case of DWSIM. There is research migration also, where the students have to take a research paper, replicate their results in that particular open source software. Then after no after all this, they are to a level where they can clear our internship and fellowship. So our internship and fellowship does not actually judge the student on the on the academic score. We actually give them a task on a particular software which they can choose. Like if they are interested in eSIM, they can choose the screening task of eSIM. They can perform that task. They can ask us doubts on that task. We will not directly but indirectly we will tell them how to go about this. We'll handhold them, and definitely our mentors are approachable, and we'll let them know how they can submit their task. And after that they can actually contribute to hackathons and marathons, different events where they earn different certificates, and most importantly I told recognition on our website. So once that recognition comes, the employment opportunities actually increase, and even it's a flag for, it's a feather on hat for an institution also, because we do not publish just the name of the student or that individual from that particular college. We also publish the name of the institution which they belong to. So they, it definitely helps them into their knack ranking. So that's my next slide, which I'll talk about the impact of the textbook companion project. So more than 1,000 institutes are working with us, and more than uh, you can see 1.5 lakhs codes are available online. So these are codes from a standard textbook. So uh, these are reusable, freely available for the public. In fact, a faculty from Nitar Bhopal is using our Scilab codes in his classroom to explain some concepts in Scilab. He's also using Scilab on cloud. So that's how we empower the institution and the students across by, without any license fee, uh, uh, without any, you will say, you can learn open source software easily, which is used in their academic curriculum. Okay, so this is the most important slide. I'll tell you the accreditation. So after doing so much, you will definitely get your accreditation comes into picture. So as per the NAC criteria, so tech enabled accreditation, where you will get the maximum grade point if you uh, do FOSSI related activity, it will come under tech enabled learning. Then student ratio for teaching and learning. So I think that also will give you score. And this is all into research and innovation, where everything is published, there are people, there's a community contribution. So I think that will also give our institution some great points. And definitely we are doing a outreach in QGIS, in a GIS project. We are actually giving the students are actually coming up with the maps where, for example, they have to show that where are nearby toilets are there. So they will actually do use our software, and they will tell us, do geographical mapping, and they will tell us. So these kind of approaches are there in FOSSI, and it definitely helps the institution get a good NAC NIRF ranking. Hope my slides are not now a problem, Sumanto.
Yeah, it's working fine.
Yeah. So next is, we make the students industry ready. That's what our main aim is. We upskill the students through FOSSI, different softwares they contribute to. And definitely instead of a classic resume, they submitting the resume, definitely the mention of FOSSI is there. But the good thing is that the employer will have a place where he can validate that whatever is there in the resume is correct. So we have a verified thing. We do not publish the reports etc on our website without verifying it, reviewing it thoroughly. So everything what is there is actual work of the students done. So definitely we actually upscale them to, and bring their capabilities through open source software, contributing into different activities, which definitely helps them build employment opportunities. Next up is how this is done. So we are cultivating competency industry. Like I said that we are bridging the gap between academia and industry. So FOSSI actually blends with the curriculum. We are using softwares which are used in the curriculum. So for example, I told you Scilab is equivalent of MATLAB. MATLAB is used. So though, and even textbooks are coded in Scilab. So the solved examples of the textbook are coded in Scilab. So we easily blend into the curriculum. For VLSI circuits, definitely you have seen that eSIM can configure, it's flexible to use. So DWSIM is also a great software for chemical engineers, where they do process flow sheets of a big process plant is done, which is a industry standard plants, and that can be easily done into DWSIM. Even I think OpenFOAM has done many such things like that. So we, these are few examples which, just to say that we are easily blended into the academics, and we know what is used in industry, which actually, this is how the FOSSI is bridging the gap between the industry and academia. Next up is, yeah, so here are a few testimonials from our contributors. So Professor Saket Chaudhary is actually, he was an alumnus at IIT Bombay. Now he is a professor at IIT Bombay. So he contributed to the textbook companion project. Akash Garg contributed to textbook companion project as well. He is a NIT Trichy alumnus, and he got placed, he got an internship in Japan. So then we have industry placements also done, where so one faculty, Professor Madhuri Kadam, she actually contributed in eSIM hackathon, and then she started learning about eSIM. She actually got in touch with us through one of the FDPs only, like this, and then she said that she is into she wants to explore more her skills. So she then slowly switched her interest from teaching to academic, and she got placed into synopsis after winning into the hackathon. So similarly, we have Mehulkar. He has submitted a flow sheet in DWSIM, and he got placed into a big company. Also, we have Sahil, who got placed into Reliance Industry after doing flow sheeting in DWSIM. So like that, there are many stories like that. So we can go on telling the stories like this. So we are having a sustainable loop where the industries can improve their accreditation by migrating their labs. Student can transform and upskills, do upskill, sorry, the students can transform, contribute, and build a good portfolios through internships and contributing to different activities. And definitely we have a pool of students where we make them industry ready, uh, so the industry can pick them easily. So that's how we are sustaining. And last but not the least, I would want you all to go back to your college, tell your principal or leads. I heard yesterday that there are many HODs also available, so you can collaborate with us, establish a FOSSI center. We will help you reach all these sustainable things and attain the success in open source software. Here, you don't have to pay any fees. You can empower your students. You can The faculty can partner with us. In fact, in CFD we have a very good approach which Payal has come up with, and his team and her team has come up with, is a faculty uh, partners, where faculty mentors the students, our interns, our contributors. The faculty is at different college, the student is here, the student is also at different college, but their interest, their contribution to open source software is the same. So that's how they connect, and that's where they build this community. So we publish their names on our website, and then definitely lab migration I've already spoke about. And you can launch a FOSSI center at your campus and make your campus open source campus and more modernized. In this way, you can write to us at info@FOSSI, and you can visit our website fossi.in. In fact, I will just go through a website quickly. So yeah, we have a GUI hackathon coming up So I would want you all to register for this hackathon. It's on Scilab, where you will have to build a GUI for Scilab. It's very easy. You can approach us. You can. So it has cash prizes, certificates, internship opportunities. Later, the top students will get selected as our interns, and all this information is there on our website. You can just check it out. So, talking about coming back to FOSSI, this is our homepage. So, it starts with Professor Dr. Abdul Kalam's quote that we should use proprietary software. That's the quote, which says that it will save the lots of money, it will help lots of people, and we will be a developed country soon. So here are different software listed. Whatever you are interested, you just click on that. I've clicked, and you will see the website for this. And there are different activities. Like I said, there is research migration, circuit simulation project. There's lab migration textbook. So you can see all that. And then we have marathons, hackathons listed here. So this is about eSIM website. So likewise, you can go to individual website depending on your interest. So these are the software we promote. Then these are the activities which we have. And these are some former employees talking good things about FOSSI. And one important thing I want to tell you is I was talking continuously about recognition. So these are the internship programs which we do. So right now, summer internship is going on. Now we will have, maybe in September, we'll announce our autumn semester long internship where the students work with us. So I will show you the summer fellowship which is going on right now. So these are the students which are selected. So this is how we give our screening task in different softwares. You can see this is what they have to do. And there is a web link where the detailed explanation is there. If they want to get in touch with mentors, there is a contact ID. So we can help them. Definitely there's rules and regulations. So these are the results of the selected fellows. So most of them are coming here. Most of them are working remotely. So these are the names, as I said, that these are the fellows selected. So this is just selected. Afterwards, when they are selected and we ask for the report of the work done, this is what you will see for these fellows. So you can see, I will pick up one eSIM guy. So you can see Abhishek Soni from Dronacharya College. If you click here, this is the report. This is what the employer can see, and see what actual work they have done. So yeah, this is it. And this totally verified. So the employer has no doubts because everything is there. And as I said, that the college name also appears. So it definitely helps the college in the accreditation. And now we have FOSSI centers. So I told you, you have to connect with us through FOSSI centers. What is FOSSI centers, how you can do it. So everything is listed here. So that's it from my side. I hope you have a good day learning about open source software. And yeah, thanks everyone. If you have any questions, we can have 2 minutes. Already overshooted the time, but I think 2 minutes we can have some Q&A if you want. Otherwise, we can go to the next section. Or if you have any doubts, you can write to us at info@fossey. We are there, and we can redirect to a different team. Thank you. Thank you so much. Over to you, Sumanta.
Thank you, Vinita ma'am, for your insightful session and letting us know about what FOSSI does. So, in our next session, we will Professor Prabhu will be presenting. So, just introducing Professor Prabhu. He is the principal investigator of our FOSSI project, and he is currently a professor at Aerospace Department, IIT Bombay, and he has lot many things in his bio. So yeah, so hope to he has done a lot of contributions to the Python and the Linux ecosystem. He has also established the Indian Linux users group in Chennai, and yeah, so now you will be hearing from him. So over to you, Professor. Professor, are you there?
Yes. Just a second. Good morning, everyone.
Good morning, sir.
Thank you for your kind introduction. Uh, so, I'm actually very pleased to see so many people on 160 people today on Saturday morning. Um, I'm hoping that the numbers will grow as the day proceeds. Um, so, I have been associated with FOSSI since its start, 2009, and I have been involved with open source for a very long time. So open source is something that has been quite dear to my heart, especially because uh, it has been something that has enabled a lot of my own research. So all of the work that I do in terms of my research is almost always open source. In fact, for every publication that we make all of our results available as well as the code available. Um, and we also do it in such a way that we can reproduce every picture that we produce in a publication. So again, open source has kind of framed my career to a large extent. Um, so, so what we've been trying to do with FOSSI is to try to ensure that every student is also exposed to the existence of open source software. And it turns out that many students do not know even today that there is a lot of open source software. And while everybody uses it under the covers, for example, I think there is no one today who does not use search engines and AI in some form or the other. A lot of these have also been powered entirely by open source. In fact, the entire AI revolution would not have happened if there was no open source software. So, open source is something that we kind of take for granted, but the instant you realize that it's something that's so important, it becomes invaluable. And it's just sad that a lot of students and sometimes even faculty do not know of the existence of open source software. So FOSSI's goal, as Vinita has very clearly told you what FOSSI does, one of the goals is to ensure that everybody is aware of open source software. So given that, I'm really happy to see such a large participation on eSim. And eSim in particular is really exciting because in the next few years, India will start building capacity on how to actually we can fabricate chips in the country. We already can, but they are at much larger scales. But eSIM is one very important piece of this puzzle. Right? So, for example, all of the devices that we use today, right, phones and laptops and IoT devices, even Arduino chips, none of them are actually manufactured in the country. Even if they're designed in the country, they end up having to be fabricated outside. So you can do the design today with eSIM, and there are open source tools that will let you go all the way to do what's called a tape out. But the actual fabs are not in the country, and so you have to go outside. But that is changing rapidly, and thanks to the the Semiconductor Mission, the ISM, of the government, there's a lot of investment, and there are new fabs that are coming out. And so this is a huge transition point for the country. So the instant we have an ecosystem where people are aware of these kind of tools, open source tools, and in parallel, there are many people working towards enabling open source so that open source can actually be used directly to do fabs. This is something that's a game changer because you no longer have to purchase extremely expensive software in order to do the fabrication. And this means you can produce designs and actually fabricate electronics components, hardware, come up with new designs, and do all of this through a complete open source pipeline. What this means is that there's an undergrad student, for example, or, or a very enthusiastic high school student, who has an idea, who has the ability to focus with all of the noise that is available on the internet today. But there's a lot of good information as well. So with this information, armed with you know healthy amount of dedicated effort, one can actually design and with a little bit of financial investment actually fabricate. So this completes that whole loop. And so this is a new nascent thing in this country for us because earlier this was simply not possible. But in a few years, this capability will be there. So it's really, really important for us to learn the good open source tools that are available now, master them so that we can actually uh, do useful things with this. So this is really an exciting time for our country, specifically our country. Of course, abroad this is not so much because fabs are accessible elsewhere, but it's still fairly expensive. Um, However, that said, even abroad, doing fabrication for smaller size chips requires the use of closed source tools. And this is again where India can play a major role by actually open sourcing the whole stack. Um, so this is something that I think eSIM is in a very unique position, thanks to the uh, vision of Professor Kannan, who I believe many of you have interacted with in the last yesterday. He is the one who actually started the eSIM project, and the various eSIM folks, starting with Sumanto, Varad, and other people in the team. Um, all of them have really worked very hard and continue to put in a lot of effort to make eSIM what it is. And we also encourage you to please, your faculty members, encourage your students to again contribute back to eSIM, make it better. Please remember this is an open source project, so there will be issues, there will be bugs you find, but the great thing about open source software is that you can fix them and you can actually have other people fix them. You can copy the software, you can distribute the software. None of this is illegal. So it's a wonderful aspect of open source software. But it does take ownership, and that ownership is now a shared ownership with all of you. So I strongly encourage you to participate fully, understand, pick Sumanto and others' brains, and make sure you understand this and see that you can try and contribute back to the open source community. And again, this is not about necessarily FOSSEE. FOSSEE is a means to an end. You can think about this as something that brings good to the country, nothing like it. So once again, extremely happy to see all of you here, and I really hope that you have a very fruitful session with this workshop. And again, Vinita has said lots of things about FOSSEE. So if you're interested in beyond just eSIM, so there are many other things as well, right? It's not, electronics is not the only thing in the world. So if you have other colleagues who you think would benefit, pretty much all of the colleagues that you have in your respective universities would certainly benefit from using open source software. Because I'm not an electrical engineer, I'm a computational scientist, and I've been using open source for more than 25 years. So a lot of us derive enormous benefit. I pretty much don't use any commercial tools for my research. So this is something that could benefit everyone. So we urge you to also spread the word with your colleagues and other students as well, and also interact with FOSSEE, because we are having plans of making sure that more and more students get to learn about FOSSEE. And once again, this is not about, we're not a company, we're a MOE run funded project through IIT Bombay, and a lot of us are doing this simply because we have passion for open source. And we believe that this will make a big difference to you. So please do spread the word about FOSSEE and engage with us. Thank you very much.
Thank you, Prabhu sir, for your kind words and letting us know about open source. If anyone has some doubts, quickly, 2 minutes, please feel free to go over the chat. A nice opportunity to interact with Professor Prabhu.
All right, so if no one has questions, I guess you can always feel free to reach out to Sumanto and the others, as well as I guess Vinita and Busha and others who are available, Payal, Shanti Priya, all of them are available. You can always interact with any of the FOSSEE staff, and they will happily help you with any of these. Once again, wishing you all the best in this wonderful journey. I have, really made a big difference to my life and my career. I really hope it does to yours too. Bye, everyone.
Thank you, sir. Bye.
Thank you, sir.
Welcome.
Yeah. Next, we will be inviting Professor Sangeeta Mangesh, who is the director of Dronacharya Group of Institutions, and she will be talking on EDA connecting concept to lab. She has accomplished a lot of things in her career, including recorded lectures in Doordarshan, Swamprabha channel, and so on. So yeah, happy to have Professor Sangeeta Mangesh. So over to you, Sangeeta ma'am.
Good morning to everyone. I'm Dr. Sangeeta Mangesh, speaking from Dronacharya Group of Institutions, Greater Noida, and we have been associated with OC since 2016, and we cherish this association. And as a part of this one, I really thank you, each one of you from FOCT, for giving me this opportunity. So, shall I share my screen, sir?
Yeah.
Yeah. So, entire screen I'm seeing. And I'll open this.
Are you able to share it?
Yeah, just a minute. I think I'm able to. Just tell me whether my screen is visible to you or not.
Yeah, it's visible.
It's visible. Okay.
Can you close this window maybe?
Yeah, I'll just 8 seconds. I'll just put it this one.
Okay.
Okay, and I'll start this one. Okay. So, good morning, everyone. This is the topic what I am going to speak on. That is the EDA connecting concepts to labs. Now, when I gave this topic to ChatGPT, the image which was given to me, again, open source access, say, whatever data I got was this one. So my entire presentation, being from the electronics and communication background, will be dealing with these kind of things, what is being reflected by the ChatGPT. So what I thought was exactly getting aligned with the ChatGPT expression, and that is why I'm proudly saying that my imagination is also is aligned with this. So my topic or the discussion pathways include, first I'm going to discuss what is the role of EDA in VLSI design. Then I'm going to discuss the design flow, different abstraction levels. What are the key EDA tools? There is overall overview of them. And then I'm going to speak on what are the available open source tools. Among them, I'm going to discuss what is the lab, like when I'm discussing open source tools, I'm giving you 2 lab examples also, which are available on YouTube. The links are also shared over there. Along with that, I'm going to give you the general concept where I'm considering some case studies wherein these EDA tools have been used. There is complete impartial thing, no mention of any proprietary software also being mentioned. Those who want to know can reach out to me or Sumanto sir, and I can subsequently share the details. But as far as this PPT is concerned, my intention is to just give you an idea how research domains can be aligned to the EDA outcomes or EDA tools, how they can benefit the research outcomes. So very first thing is dynamic shift in VLSI scaling. Now, what does that mean? Initially, we were having only 2 typical laws. First was Moore's law, and second was the power scaling law. So these 2 laws were governing the entire VLSI domain. But when around 1990s, we first found the multi-chip modules, and with this multi-chip module, since single package was comprising of multiple functionalities without increasing the chip complexity, the new paradigm shift took place. Our different aspects started, wherein we have system in chip package, subsequently RF module, and reaching down to heterogeneous integration or disaggregated SoC or photonics chips. Now, in this case, you have different kinds of, like, this is how the evolution is going ahead, integration of AI, and all these things are impacting the overall VLSI design. And therefore, technologically, there is complete shift in the aspect in which the design is being done. And that is why it is very, very important to consider this more than Moore's law concept. Now, what are these 3 main concepts which are being considered in that particular as an outcome of that entire figure? The new paradigm shift took place because when we started exploring the alternatives to classical silicon-based architectures. And this happened because of the extreme scaling of the devices, neuromorphic computing technologies being added, that is mimicking the human activity or human brain. We started using the advanced materials, investigating revolutionary alternative substances to silicon, wherein you had 2D graphene monolayers, high frequency wide GaN semiconductors to surpass the physical silicon limits. After that, we have third aspect, that is design paths were looking beyond the traditional CMOS technologies, replacing conventional charge-based switches that have acted as the foundation of computation for decades so far. So beyond 2000, a modular integration frontier got opened, and there were advancement with 3D IC, vertical chip stacking, chiplet technology, where modular distributed die systems were being used. These were these emerged as these structural post-CMOS solutions to pack and interconnect transistors cleanly, safely, and efficiently. As we all know, VLSI is basically entire design methodology is now precisely or compactly mentioned by this Y chart, where three different domains of Y, three arms of Y are represented by behavioral, structural, and geometry. So each domain is also like at each arm of Y, you have something known as abstraction level also, which is enhancing the, or which is basically increasing the complexity of the design as you enter into higher level of abstraction, like as you get deeper into the level of abstraction. So therefore, since the need for EDA tools can be discussed, the VLSI metrics which are driving EDA usage is basically because of the interconnect delays, crosstalk technology constraints, which are hampering the time analysis or routing placements. Second domain is the power optimization and performance optimization, 3 Ps you all know. Then thirdly is the handling antenna and antenna rules, clock skews, issues arising due to reuse of IP cores. And lastly, reliability issues, which are basically thermal migration, electrostatic discharges, and all these things. So these complexities involved in the IC design at the nanoscale domain basically gave us the it made us compulsorily to use EDA domain first prior to implementation. It also, we also know that the VLSI design window is so small. If you consider the revenue potential, unless and until you have your chip within the given time frame, your entire yield is completely, like financial yield is totally dependent on how fast your chip is going to be in the market. When the need arises, it is similar to the person manufacturing umbrella, and if it is coming in the before ahead of rainy season, it will get sold. Otherwise, it is not being sold. But the window for umbrella is for three months. Within that 3 months span only, it will be sold. So similarly here, the window span is so small because the technology advancements are so rapidly changing. So widely, this particular things are being happening. So unless and until there is need during that time, if your chip is available, it will be used. If you take longer time to market, and also at every stage of manufacturing or fabrication, the cost escalates 10 times. That is why the shorter design window, due to shorter market window, a higher risk is there involved. Delayed release directly impacts the profitability or yield. Revenue opportunity window is basically very, very small, and therefore this basically gives you the criticality of EDA tools. And this is what is being discussed over here. So since engineering backbone of semiconductor industry that enables design, simulation, and verification of modern billion transistors within an integrated circuits, this is basically very, very critical to use EDA tools. As we all know, they reduce the time to market, lower the developmental cost, and also first pass silicon success is that can be achieved. So graphically, we are showing the entire design automation, simulation analysis, functional verification, and performance optimization. These are the 4 core, what you call domains, under which these use of EDA tools is very, very critical. Now, what are the types of EDA tools? This is overall, in general, what we see. So in general, when you consider the VLSI domain, there are multiple categories of EDA tools, but broadly they are divided into 3 categories. One is based on design methodology, that is how your design is going to be, whether it is FPGA structured or standard cell design or full custom design, semi-custom design, all those things. Secondly, based on the design flow, and thirdly, based on the type of model you're going to deal. That is, you're going to have performance model, timing model, system model, and all those things. So these are the 3 broad categories of EDA tools. Again, if you consider the entire domain of EDA, that is electronic design automation, there are 2 circles or 2 aspects of it. One is technology assisted computer aided design, and second is the SPICE. So these are basically technology aided tools where we have something known as a process where the fabrication processes are being optimized. They mimic the entire fabrication steps. Secondly, you have something known as device TCAD, where you're designing the device. And thirdly is the interconnect TCAD, which is basically giving you access to design the interconnect between these devices, what you have designed. Once you have this entire structure design, then you go ahead with its implementation through SPICE, and then you actually integrate your circuit. Again, there are certain things which are known as front end and back end. So this is entire design flow which is being represented, wherein initially you will go for system specifications, then you will go for its architecture, you will design the functional and logical aspects of the structure, whatever design you want to achieve. Then actual circuit you will try to mimic or try to check, test. Then how you are going to, for example, if I want to have an inverter, and if I want to have basically NAND gate. So first I will have the NAND gate timing specification, what is the delay I want, all those, where am I going to use it, what are the input, how many number of inputs are there, how many, it's just simple example I'm giving. Then you have something known as physical design of that entire structure or the circuit, what I'm going to implement. Here I will have partitioning, floor planning, placement, clock tree synthesis, signal routing, timing, all those aspects I will go ahead with during the physical design. Once the physical design is over, then I need to verify it. Whatever I have designed, whether it is falling into my, or it is exactly following my requirements, whether it is in adherence with my timing considerations, that I need to check out. Then only it will be accepted for fabrication. Once it is fabricated, packaging is another aspect which is to be taken care of. It will be tested, and then the actual chip will be brought to the market. So entire this design flow, we all know. But when we consider this design flow, you have something known as in reliability using TCAD. It's always very, very important during this fabrication process. You start the fabric specifications right from the fabrication steps. You design the process development kit, that is, you entirely design the process. You specify the parameters for the fabrication steps also, and you have EDA tools for that also. Now here you will have SPICE, lib, layer formation, entire information for PDK will be like within the PDK, it will be available. It will have process simulation. Then once the process simulation, that is within that circuit, like you have in our FOSSI also, we use 130 file, 130 nanometer file. So 130 nanometer file will have all the process parameters associated with 130 nanometer technology. So considering those technological parameters, my circuit simulation will happen, and all the aspects of 130 nanometer technology will be considered during my circuit simulation. So this is what is being shown in this particular slide. Now, what are the front end and back end tools? So front end design is basically concerned with functional specifications of the system, while back end design focuses on physical implementation of the design. It also, front end typically performs the architects, register transfer or RTL level, whereas back end is basically a physical designer's job and computer aided design engineers will will be involved in designing it, performing all the assessments at the back end. Front-end design typically is done at high design level languages, while back-end design uses specialized CAD tools and algorithms. Additionally, front-end design phase is typically done at higher level of abstraction. If you remember the Y chart, higher level of abstraction will be having the front-end part, will cover the front-end part, whereas back-end is more complicated, more in detail, focusing on the physical implementation of the VLSI chip. What are the tools? Now, typically, what are the tools which are being used during these processes which are involved in chip design? So, specifications will be done at system level requirements. Then you will have RTL design, where Verilog or hardware description language will be involved. Functional simulation can be done using a simulation tool such as Model Sim, Verilator. Then you will have synthesis of what you have designed, whether that functionality is as per adhering to your norms or not. That synthesis you will be doing. Then you will go for the floor planning. Then you will go for design rule checking, whether your design is in adherence with the layout norms. Those things will be taken care of by the LVS. And then your GDS2 file will be created, which will be ready for tape out and fabrication. So these are typically tools, or these are the typical tools. I cannot say that these are the only tools. These are the in general tools which are used for different stages of VLSI fabrication or for chip designing. These are the typical tools which are being used. And of course, our open source FOSSI is a pioneer in providing you maximum flexibility, and total credit to this particular team FOSSI, which is giving us all these access to all these fabrication tools. Now, typically, like I'm just giving you the brief, since we are going ahead with the EDA and we are mainly focusing, like my focus is mainly on the open source EDA ecosystem. The typical tools, what students and faculty members can usually use to start with their lab work, or to start or to experiment, that is realize their concepts into reality. So that those tools include YOSYS, which is again open source synthesis suite, supports Verilog, produces netlists for FPGA and ASICs. There is Verilator, it is a simulation tool. Then you have ICARES Verilog, which is accepting Verilog. Then you have something known as Open Road. All the links are available in the last slide. If anybody is interested, can very well go to that link and visit that link and explore whatever is available. Then you have KiCad, which is PCB and schematic. So you can have schematic, circuit schematic, and electrical simulations you can do for any design, and you can have the PCB design flexibility also. And lastly, DRC and layout can be verified using Magic VLSI. So there are multiple Magic VLSI tools which are available. Okay, one of them is like layout ke liye you have other tools also, such as K layout, which is again open source. But then this is a typical tool which is usually used. Now, what is exactly the meaning behind concept to schematic? So when I'm going ahead with the concept, so design entry starts with the concept. So whenever you are having some concept and you want to implement in case of ASICs and FPGAs, that is, you want to go for digital logic implementation. Very first thing is you write or mention your functionality using Verilog. Secondly, you go for behavioral aspects of your design. Then you use entities for hierarchy, parameterize for reusability of those entities what you have defined. You write the test benches for validating the functionality, and then you go for the synthesis. In case of schematic, you first design a circuit schematic, we call it as a capture, where the circuit is being created as per your requirements. Then you go for the component selection and footprints. Footprint means the technology node, what you want to use, the typical logic, like component library, which is supporting that, you will be taking into account. Then you will create the netlist. You will run the electrical rule check, and then you will link that particular circuit to PCB layout. And subsequently, you will go for routing. So this is what is the conceptual implementation of either your logic design or conceptual implementation of your circuit design. So PCB or analog domain design on one side, whereas a digital, ASIC, and FPGA design on the other side. So when we are discussing about concept to lab, this is the first example I'm considering where there is open source tool which is being used. What we mentioned just now, same IKRS that is being used, and that particular thing is being used to implement a counter. Now this counter is designed to count of 4, 3 to 0, and then on the positive edge of clock, the counter is being designed. It is available, freely available on YouTube on one of the NPTEL courses from IIT Delhi, and this is part of that. Its link is already provided. So this is the test bench that they have defined. This is the test bench code which is being shown over there. My effort or my intention is to just show you how many ways these open source tools are available. I'm going to give you complete access or complete idea about different aspects of open source tools which are available or accessible to each one of us, and we can incorporate them as a teacher into our day-to-day teaching. So this is how the test bench is being done. There are other alternatives also for Verilog or hardware description languages, which include GHDL, you have NVC, and GTK Wave. These are the other alternatives also, apart from what I have mentioned over here. And this is what is the result of your 4-bit counter, which is being simulated using open source tool. So this is an important aspect what we can incorporate in our labs while teaching. So this is what is the concept implementation through open source. Second example I would give from the FOSSI only, where this RC filter is being simulated, RC circuit is being simulated, the schematic is being shown, and its Python scripted output is being shown over here. So this is also available on FOSSI website, YouTube website. Everyone can access such circuits. They have very beautiful explanation by Karsar, where he is explaining each and every aspect of design. We can implement such circuits and we can show them, encourage students to use them so that they can get their concepts clear in their minds, and they need not have to struggle with the components also. Prior to struggling with the components, they can check out the circuit, verify the output, and then they can rig it on the breadboard and implement it subsequently. So this is also one of the example what I would like to quote. Here, these are the outputs which are being shown. This is the capacitor charging, discharging being shown over here. Now, people underestimate the what you call open source tools. So here I have used one of the proprietary tool, but I have used the same concept which is used in KiCad. KiCad is open source tool. Its spice code is done in open source manner. But I have used a proprietary tool to use this KiCad open source. Again, I am saying you, open source tools are very, very, very good and very efficient. And this is the manner in which I want to highlight the strength of the open source tool. They can be very well integrated in the proprietary tools also, wherein from this KiCad spice, what you call code, I have designed a symbol. Then I have designed an amplifier, and same output I have used in the proprietary tool also. So please understand, this is how your open source tools are so much adaptable, so much effective, so much they have so much strength that you can initially go ahead with the open source tools. And for higher research domains, if you want to progressively go for the higher end analysis or something which is apart from what is being not supported by the open source tools. There you can fetch your data and then work ahead and proceed with the next step, like higher hierarchy levels of this. So these are the EDA tools. Like I'm just giving you the research domain also, full of EDA tools. It is entire thing. EDA tools can support the different research domains also at the device levels. You can have fabrication. Initially, this design was also done using open source tool. Then it was brought onto the 3D or what you call the proprietary tool. This was my own work way back in 2017, which when I designed this particular 3D MOSFET, that is FinFET, on 20 nanometer technology. And then I realized it. Initially, I designed it using open source tool. And then subsequently, I brought the data onto the proprietary tool and the this one. So similarly, these are the advanced stages when you want to do, then only you need to go for the proprietary tool. This is what is the research domain I want to highlight. And this is how I want to highlight that you can go ahead with advanced research steps or advanced, if you want to focus on advanced stages in the research, then only you need to go for the proprietary tools. Prior to that, you can very well go ahead with the open source tools and carry on. So these are the advanced features what the researcher can go ahead with using the proprietary tools. This is, I'm highlighting this also because this was the way or the layout thing which was which is being projected or presented or reported by our SCL Mohali team. We have Foundry in SCL Mohali, and this is the paper from SCL Mohali team, which I found and I thought I should discuss with you, because here they have used, though they have used proprietary, but the approach is totally different, because it will give you a new idea where they have worked on the placement of the particular device to mitigate the total ionization dose effect. That is, when the system is being used in RF region or space, this thing where there is ionization dose or it is exposed to different environmental impacts, if you want to study, then reliability aspects can also be verified in this particular manner. So this is also one way, this approach, where EDA tools can help you to perform higher order of research results. So this was about the conventional MOSFET, what is being designed, and this is about the L-shaped layout, where they have worked on the device layout. So initially there was structure, then there was advanced structure or the advanced fabrication aspect, then this is advanced layout structure. So these are the aspects where your research can focus, and as a part of this research, they have claimed that N MOSFET behaves similar to N conventional MOSFET, because radiation effects of 300K dose due to electron hole pair generation and local oxidation effects also they have considered. The threshold voltage changes direct path between the source and drain, resulting increased in the leakage current, and therefore leakage current was at the order of 10 raised to the power 8 at 300K radiation dose. They have identified that digital circuits employing the radiation hardened MOSFET for specific critical applications have mild degradation in the operation frequency on account of increased parasitic capacitance as compared to design employing conventional MOSFET in a layout style. So my intention is to give you an idea that how effectively we can use EDA tools for different research aspects. I'm again saying you, these are not the only ones. I'm just giving you some examples. Another approach of research may be on the circuit level or schematic level, where the authors, and again, I'm saying you, these are the authors which are at MTech level or BTech level who are explaining. He is one of our faculty who has worked with DTU, like in DTU on his circuit. And that is how we are, like I'm quoting his example over here. He has designed CMOS linear resistor or floating resistor, and he has configured its application also using EDA tool. And now within 1 week or request, like within 1 month or this, we are again simulating, like halfway through we are. My intention was to give you this simulation on FOSSI eSIM. So we are implementing this on FOSSI eSIM, and then I'll circulate, like I'll share the same results with Cursor very soon, because we will do this exercise and share, because the team, our team is working on this. So this is basically a proprietary tool, but same things we will reproduce in eSIM, and we will effectively share with FOSSI team. And this is what is our job currently going on. Similarly, the research domain on eSIM can also work like hardware description, where you are detecting, okay, CN accelerator for real-time object detection using YOLO 3 with the DARKNET 19 architecture. So here they have used the architecture level HDL structure, and they have implemented using, this is also one of the latest focus on the research being deviated. And this is what is one of the approach where EDA tools are supporting high-end research results. Now, what are the future trends? So future trends, it started with computing with physics, slowly increased to intercrossing computing substrates and models. Then we have intelligent authentication. Then we started on sensors, on parametric modeling. Along with that, we had probabilistic modeling or probabilistic computing. Then we started, or then the paradigm shift took place, and we had self-aware AI, intelligent IoT, managing big data in design, and slowly we are going towards incorporation of EDA tools equipped with AR, that is artificial intelligence. And this is what is the thing. So when we are using these EDA tools, what are the common pitfalls and how to fix them? So this is the thing which I wanted to express, or I wanted to share with everyone. Whenever we are simulating, never simulate without assertions. So whenever you are having some assertions, include those into Verilog assertions, and then use them on catch all those silent features. When you are designing in digital domain, please ignore the latch interference warnings. Always code combinational logic with full case, if else coverage. Never skip GLS after synthesis. Always consider the gate level design is correct. Consider or run the gate level synthesis, and then only go for finalization of your this one. Never edit the synthesized netlist manually. Modify only RTL. Resynthesize. Netlists are the tool which are giving you the outputs directly. So never edit the netlist once you have synthesized your data or synthesized your circuit, whatever your schematic or your circuit is. No version control for HDL. There is no version control in case of HDL. So always tag clean sim milestones before the synthesis. Using, it is not always good, like always there is no rule, hard and fast rule that you should use the proprietary tools in the labs. First, you should always go ahead with the open source tools. Prototype, okay, portable, zero cost, FOSSI backed. They are very, very good tools. They are user-friendly tools. So go for them, and then only go for higher end tools. While searching the data, I came across a very good article which was giving you the idea on how our semiconductor, like India semiconductor mission is going to succeed, and what are the pros and cons ahead of pumping in so much money into it. So very good article was written by one of the VLSI professional, and in that he mentions the success of India semiconductor mission in long term has to be built on accessibility, scale, and openness. And here the EDA tools are not, this open source EDA tools are not going to be the replacement for commercial tools, but they are necessary foundation for inclusive education, grassroots innovation, and creation of robust domestic semiconductor ecosystem. As a part of building up this ecosystem, we must recognize open source EDA tools as a core pillar of semiconductor education and research in India. support open source design flows at national and state levels for teaching, research, and prototyping. Direct funding towards closing gaps in open source EDA toolchain through academic and community efforts. We can work towards it because we are all faculty fraternity and we have complete set of large pool of students who are there, who are attached with us. So we are the basic source of this direct funding. Integrate the end-to-end open source chip design projects into university curricula. Whenever we are doing, even if they are not integrated, we are not like, try to encourage, motivate students to take up some projects, mini projects based on that, so that they can effectively utilize, become friendly, and subsequently when they get into the market, prior to that, they can they can have their hands free on the proprietary tools also. Incentivize collaboration between academia, industry, and open source community for relevance and sustainability. So what are the core takeaways of this particular session? So AI is going to have complete revolutionized EDA domain. Operational boost is going to be there because AI-driven EDA tools will enhance the automation, scalability, and interoperability. Research focus will have rapid adoption of machine learning, data science, generative AI, and modeling as well as optimization. You have efficiency and design exploration, where you will have innovation in the cycle. Advanced EDA tools directly will boost the accuracy, efficiency, and overall chip innovation. On broader horizons, by enabling faster and cheaper design cycle, all VLSI professionals can fastly expand their design exploration boundaries. Transitioning from design and technology co-optimization to system technology co-optimization will only be possible using our EDA tools. Holistic optimization, that is emerging from multi-die system to system technology co-optimization, shifts the focus toward optimizing the entire system, simultaneously balancing the technology, die, and packaging vias, integrated multiple objective analysis. So this is also possible only with EDA tools, which are giving you all advanced features to verify or validate these things. 3D heterogeneous integration is also possible because it is with AI and multi-chip module technology, or 3D design is like stacking of devices is being happening. And with that, 3D integration rises the modern EDA tools. They have become absolutely crucial for accessing complex physical variables, which include use of new materials, enhanced thermal properties, because power, packaging is like power and performance are crucial when you are scaling and designing the 3D integration, integrated chips. And thirdly, the stress factors, which is related to thermal stress and with effect of aging. So these are the suggested links, what I would like to share. These are the typical links which are being used usually. And this was all about my sake. Now over to you, sir. If anybody is having any doubt or anything, you are most welcome to talk to me. I just gave you the overview of different research domains. I hope it was useful to you, and emphasizing the open source tools and their importance in VLSI domain. Over to you, sir. Bharat Patil, over to you.
Yeah, thank you so much, ma'am, for the wonderful talk on connecting EDA tools. So for all of the participants, we'll be sharing the attendance link for now. Ma'am, there are some questions in the chat. Ma'am, your mic is off.
Let me know. I'll just. Device modeling. Ma'am, these are proprietary tools which I have used. There are multiple tools. You can search on the net. There are multiple tools which are available.
Yeah.
Anything else? You have TCAD. You have TCAD, open source TCAD also available. And once again, if somebody wants to check out, you can go for nanohub.org. It is very good website where you can have multiple, like there are multiple lectures and physics-based simulator, like open tools also. Create login on nanohub.org and you can explore multiple things. Whatever queries you have in your mind, you can explore those. It's very good thing from Purdue University. People are more concerned about their attendance, I think. Bharat sir, you can go ahead. So shall I sign off?
Hello, madam.
Hanji, yes sir.
Madam, if you can just type the link, if you can just tell me that is nanohub.org, you said just now.
Yeah, I'll just, 8 seconds. I'll just. I'm just typing it in the chat box, sir.
Yes, madam. Yes.
Eight seconds. Just give me 1 second. You have multiple courses also available on this. There are books, references. It's a very good website for beginners, basically. And not only that, for first year students, I tell them to use those Java appellates also, which are falstat.com, if you are aware. It is also free of cost. falstat.org करके एक website है, like you can use that also. FALSTAD. You can ask the students to explore, basically. Apart from our, like your FOSSI website is exceptional, but for electronics engineering students, if they want to explore, especially first year students, if they want to explore something, this website is also very good, Falstat. It's also open source. There are, I have mentioned all of them onto my PowerPoint slides. And if he wants, I can share my slides to you. You can, or you can get in touch with them. I'll share with you, no issues. Okay?
Yeah, all of the resources will share.
Yeah, I'll share so that you can share with them. The resource list is already like huge resource list I have put up on my slides, so they can very well use them. Open source tools, all of them are open source tools.
Yeah.
So shall I sign off? Sign off?
Yeah. Thank you so much, ma'am, for the wonderful session again.
Thank you.
Yeah.
My pleasure. Thank you to Sumantokar sir also. Thank you.
Yeah. So we'll begin to the next session. Like as of now, we are at the pre-lunch time. Like our lunch will be begin at 1 to 2. But before that, we have like good 1 hour. Yeah, we'll be sharing the link soon. Our outreach team is there to send. Shanti will be coordinating with her, and we'll be sharing the link soon. In the parallelly, so now I will discuss one good and important thing about eSIM. Yesterday we did the installation. So I hope out of these 200 people, most of them will have eSIM install on their workspace. So this today's session from this 12 to 1, we will be focusing on how eSIM actually works. So I will share my slides. Deepak ji, if my like screen or something is not visible enough, then I will turn off my camera.
Okay, Bharat.
Yeah. So for now, I shared my screen. Okay. I hope now screen is much visible and me too. Is it?
Yes, it is visible.
Yeah. So talking about the software interface, yesterday we already installed most of them, and now I will talk about how actually we'll getting started. And this today's hands-on like this for 1 hour, I will taking a very small example that we already took yesterday for the installation. But that thing was something from example. So now we'll do it by ourselves so that you will get to know how exactly the flow is for the eSIM. And after this, we have the post-lunch session from Indrajit sir on the analog design part, and then later we will be talking one analog circuit also that I will be discussing. So as you can see on the screen, this is the main eSIM GUI, and which is powered by some very good open source tool like a KiCad and many more that we have integrated with. Uh, I changed my slide. If you can see on the left side, I have put up all the important function of the eSIM. One is the schematic design. Second is KiCad netlist to ngSpice converter. Third is to simulate. So what I'm trying to say, you need to try to remember this symbol just because the symbols are particular function. So as you can see, the first interface, the GUI on the left panel, there are some tabs. So this tabs or tools option, I'll be calling at first one is schematic design. To create schematic, we'll be using the first icon. Second is KING, means KiCad to ngSpice tool, where it converts the KiCad netlist into ngSpice, so we can do process that schematic, and we can process the we may do the post processing for that. After that, there is a small diode which is like a photo diodes, and that is used for the simulation, that option. And then I will talk one by one. So let's move to the next slide. So now I want everyone to first listen to me, and then I will again uh, give some time to do a hands-on. So for that, as all of you knows that this is the recording, this session will be recorded and will be available on YouTube. So that now I will process some ideal steps, and so that whenever you are doing the hands-on, you can follow my steps one by one, and that will be very great to get things done. So I just hope my screen is still visible and my voice is clear.
Yes, Bharat.
Yeah. So on the very first, as we install eSIM, now eSIM icon is there on the desktop. That desktop icon you need to click twice. Once you click on that, this kind of eSIM logo will be appear, and it will ask you to choose your workspace. Yesterday we did choose our workspace to the example folder, or you can take any workspace. That's on you. So as discussed yesterday, the workspace should not consist any space. Most of the times, and we found it yesterday also, many of the participants has their first and last name separated by the space. So that space should not be there. If there is a space, then we will encounter some issues and errors in the while exploring the project. So what we will do, we'll keep the workspace as simple as possible. Simple in the sense we will won't use any special characters, and we won't give any spaces in that. After that, we'll just click OK. Now I'm trying to show you the flow, and then I will show you directly on my screen. So as everyone can see, this is the interface. So this interface has some parts. On the top part, that is the menu bar, where we will create a project. We can open the project that is existing before. There is one icon called briefcase to change the workspace. And on the left side, now you can see toolbar. So now onwards, whenever I see say click on a toolbar, it means I'm talking about this vertical toolbar where all of the schematic and other functions are listed. This white portion is called Project Explorer, where all of the project will be listed out, whichever you have opened. To open any project, there is two option in the menu bar. One is create project and one is open existing project. Okay. So on the right hand side, you can clearly see there is a big dock area. That dock area is for the welcome screen, obviously, but whenever we are doing any post processing, this dock area will be having multiple stacks on that, so that you can actually change the values, change the parameter, you can select the way of analysis you are going to perform. Everything will be added on the dock area. At the bottom of that there is a console area. Console area means whatever you are doing on the eSIM or whatever happening to your eSIM, that will be appear line by line in the console area. This is the eSIM GUI. So I want to everyone know, one is eSIM GUI, that is this white one. At the back side, whenever we open eSIM, there are two windows pops. One is the black one, which is the eSIM terminal. Other is the GUI. So whenever I will talk about GUI, you everyone need to open this GUI. After this, let's now talk about the functionalities, the tool. First is open schematic. Whenever we created a project and we want to open a schematic, we want that canvas where we need to add the components and we need to design. So therefore that the first option is the open schematic. This is the symbol of that. Second is convert KiCad to ngSpice. Whenever we done with the design, once we done everything, the design should have spice model in the backend, and that will praise uh, to the main eSIM GUI, and where we will assign more parameters. We will assign the way of analysis, and then we will doing the simulation. That portion is called KiCad to ngSpice. That is converting the KiCad netlist to the to get praised by the ngSpice. Now third one is simulation. Once we done first and two, there is a direct step to simulate it, whatever we did. For that, you will click it here and it will ask you for two type of simulation. Simulations, type of simulation in the sense the way to show the simulation. Way to show the simulation are the two. One is through ngSpice and one is through Python plotting. So ngSpice is specially integrated to eSIM so that you can use ngSpice terminal to do more advanced simulation. You can do more advanced things from that ngSpice terminal. And if you just want to see the output and if you don't want to be in more advanced things, so eSIM has a Python plot, so you can say just no and you can get a waveform from the direct eSIM GUI from that dock area. Now there are some more feature called model editor, sub-circuit feature, ngHDL, Modelica converter, and open app optimization. For today's session, we will limit it up to the first three so that uh, most of the participants will be get to know how exactly the flow is. And once after that, day by day, we will increase the complexity and day by day, we will increase the feature of eSIM so that entire eSIM will be covered and everyone will get the benefit. So now I will change the slide. So this slide says three important steps. One is schematic, second is king. King means KiCad to ngSpice. Third is simulate. These three steps you just need to keep in your mind that these three steps you did so that you will get output. So now I will talk one by one. Schematic. So whenever you click on that open schematic option, which look like this, it will pop up this KiCad interface. See, eSIM is on the front, that is the eSIM GUI, which will integrate everything. But to draw something at the back end, this function will call KiCad to give the dock area, to give the canvas, to put the components and do the upfront things. So this is the open schematic. Now, whenever you click to KiCad to ngSpice, these three analysis type will be appeared on the dock area on the eSIM main GUI, where one is AC, DC, and transient. And with whichever you will select, the below things will be changed. For AC, it will change, for DC and transient. And you can see there are some tabs in that particular module of KiCad to ngSpice. Those are first is analysis, source details, ngSpice model, device modeling, sub-circuit, and microcontroller. So analysis means which type of analysis you are performing on that design. Source details means if in that canvas you need to give the values to some source, you need to give values uh, to many other components. If in case you don't want to give the fixed values to that component, you can left it as it is, and once you get back to the KiCad to ngSpice, this console give you an option to add those values here. So this way you can uh, troubleshoot your circuit multiple ways, and for that you no need to uh, design it again and again. So this way it saves you time. Third is ngSpice model. So whatever ngSpice model you, if in case your circuit has some ngSpice model, that only option will give you the option to add. In case if you take a ADC or whatever component that we have in the eSIM, if you want to tune it according to your application, so this is the option for that ngSpice model. Then is device modeling. Whatever see device, very easy way to say device is whatever basic component like diodes, MOSFET, transistor, this I'm calling it a device. So if you want to design your own device or whatever circuit that you make on that canvas, let's say there is a Huffer rectifier example, there is a diode, that diode is a normal diode. So it will perform a normal operations for a normal voltage. In case the application is for power electronics, we need to have a power diode in that. You can change that model to have the flexibility to change that normal diode to the power diode. That option you will be getting from this tab called device modeling. Then there is the option of sub circuit. If in case your big canvas has a very much complexity and you want to make it more clean, so you can do one thing, you can make up parts of that canvas, part of the canvas in the sense part of the circuit, and those parts we will save as a sub circuit. And whenever we are testing a final version of the circuit, what we will do, we will add those sub circuit one by one. So adding those sub circuit means adding those block. So those block we call as a symbol, and those internal circuitry we call as a sub circuit in the eSIM. So when in the upcoming session, we'll talk about how to create symbol. Many more things are there. We'll go next microcontroller. Same thing. We if want to add something, this gives an option to add those things via the path. Two things are done. One is the designing, that is the main part. Other giving a proper parameters to get things to get the things perform is the important. Now you want to simulate. To simulate the third option, you can see the LED, the diode, photodiode. You need to click it once. So it will ask you one dialog box. As you can see on the screen, there is, do you want ngSpice plots or not? As I said, ngSpice plots are for better like better UI, or if you want to do some better things, if you want to compare some different parts, if you want to take two output together, if you want to stack it, or as many of you knows ngSpice how ngSpice terminal works, so you can directly put those command and you can arrange those waveforms like that. But this isn't like an optional case for you. If you say yes, it will pop up in this space and you can perform uh, whatever things you want to do. But in case you are a beginner, I'm not saying beginner. I'm saying if you don't want the ngSpice, you don't want that terminal of ngSpice this that, then you can say simply no. After saying no, eSIM main GUI, that white one, as I said, the dock area. This dock area will have the option to select the waveforms of the completed simulation, and you will directly select the waveform, the branch, and you can plot the output. So I recommend to say yes, just because you can see both of the plots together. So it is better to say yes or is up to the user. So now we know the flow. Flow is to design, to add the parameters, to simulate. But the question comes, what are what are the library that eSIM is providing to the participants? Participant in the sense the users. It may be a faculty, it may be a researcher or whomever the electronic enthusiast is working on our tool. So I just want everyone to make a note of this page. If you can take a screenshot, you can take, because these things I will be talking again and again. This is an integrated library. So I will talk for a minute on a library of eSIM. eSIM libraries is divided into two parts. One is the library which has a spice model at the back end, so that we will use it to simulate the things. And that is the main function of eSIM. At the very, as Professor Kannan spoke about that, how eSIM grown at the very early 10, 12 years back. It was from the keycad, where keycad was able to show the symbols but can't able to process the simulation, and we come up with the solution that the spice model will integrate with the symbol and will press it, and then that keycad to ng spice can be used to assign the parameters and we can simulate it. So we keep both functionality in the eSIM for now. One is having the models with having the component with spice model at the back end will be used to simulation, and the rest of the symbols that KiCad has by default, we will use it for building the PCB, because all of the components which are there in the KiCad don't have a spice model, but all of them have a footprint. So every one of you are aware of footprints for the PCB that are also important, and the spice model are important. So we divided it is like whichever library is separated by a name called eSIM underscore, it is for the spice, and whichever not, it is for the footprint. It is for the PCB point of view. So you can either go in the setting preference and you can disable all the symbols which are not eSIM underscore to focus on only simulation, or you can directly use it as per your experience. So the final conclusion is, now onwards we'll be only using eSIM underscore library that I will show, and these are the listed below: eSIM underscore analog, eSIM underscore devices, eSIM underscore digital, and many more. Within this drop down, if you click on eSIM analog drop down, you will get a list of analog components that eSIM analog library has. Now most of you will think that what are there on the right side: add a symbol, add text, add a junction. I just ask one thing to Deepak sir, my voice is clear, right?
Yes.
Yeah, and screen also.
Yes, well.
Yeah, yeah. So many of you will think, what is there on the right side? What is this? Add symbol, add tag, add junction. These all things are important for today's hands-on. There are still many of the basic to advanced feature of eSIM that you can use to make the hands-on easy to understand. I have listed something. First, add symbol option to add a component. You got a free canvas. Now you want to add the symbol. How you will add? Either you will press A in your keyboard, or on the right side you will see the symbol called add a symbol. Okay. After that, there is the add text. To if you want to add something text on the canvas, you can do. There is add junction to, if there are two lines intersecting each other. See, in eSIM, I'm particularly explaining, if there are two lines intersecting, they will not connect by default. You need to press a junction on that, then only it will connect. Let's suppose there is this horizontal line and vertical line perpendicular to that line. If you just draw it, then it won't connect. It will just draw a line over that horizontal line. But if you want to connect that vertical and horizontal line, you need to add a junction there. You can directly double click on that wire, or you can use the function called add a junction by pressing J on the keyboard. The one is add a no connection flag, the cross. That in the afternoon session, this is very useful. Many of them forgot to add this, and then the ERC electrical rule check, when we do it, cause error. Just because if you don't want to connect anything in the simulation, you can't actually keep it open. You need to say this is not connected. So this add a no connection flag will give you that facility to keep that wire open. And lastly, the add a connected graphic line. If you just want to annotate something, so you can use. So for the hands-on, for the today's hands-on, these are the 5 main components to be used. As all of you have installed eSIM, I hope, and we already discussed one example yesterday, that is of half-wave rectifier. And as everyone know, half-wave rectifier has one AC, one diode. When we press the AC from the diode, it cuts the AC in such way that we will get the DC output. We can add a capacitor to make it add it as a filter. Many things are there, but for now, I just making it as small as possible to everyone can do the hands-on. So one is the sine, diode, a resistor, one ground, and a plot. We are not using any random components here. We are specifically using eSIM underscore D. That is eSIM underscore devices library. Within that, the particular component eSIM underscore diode that we design, we have a spice model in that. That's why it will run. Second, eSIM underscore R, then eSIM underscore GND. And to plot something, we will using a ngSpice, and we have a Python plot. to to software get known which branch is what, which branch is the input branch or output branch, that we are known but software don't. So we need to say to say it, we need to add a plot over there, plot v1, that we will add for the voltage, and for current plot v2. For now we'll stick to the voltage one. With this we will use one global level. Global level I will talk in the next slide. Now these are the component. If you want, you can take a screenshot of it, because this will be used, and parallelly this is a recorded session, so in YouTube you can go back. After adding the plots, that particular net has to say something, like whether this net is an input, output, bidirectional, tri-state, or passive. What is that? Because if you randomly sorry, if you just say that this plot we added to this line, then in the eSIM you will get lot of branches, but how you can define which is input? For that we'll use the global level. And for ngSpice, it is mandatory to use. If you didn't use the global level and plot, ngSpice won't plot anything. But Python plot will plot. But then you need to find which net is what, which net is doing what. To avoid such things, we label it. For that, this symbol is used at the right side. I will show. But for now, you just focus on the symbol, how it looks. It is like this. Now we have a very good understanding of everything. Now we can go directly to the schematic. I will show it. I will just give a quick recap and then I'll go. First step, open schematic. This window will pop up. Then we will draw this design. This is the half-wave rectifier. One sine is there, one diode, a resistor. Then the circuit is completed. The plot v1 and plot v1 and v1 means that plot is called v1 only. So to annotate that u question mark is there. Whenever we annotate, it get annotated as u1, u2 by default. Or if you want to add it something like something as per your application, you can do. Application in the sense it's just like a annotation, just for to know which component has which number. Also, below that plot V1, this IN is a global label that you will be adding, and then we are good to go. The register has 1 kilo of resistance, the ground, the sign, and the diode. And after the drawing this thing, this icon R question to R42 means there are some component like a register which has two question mark, means which don't have any numbering. Once we click the annotation, this pop-up will appear and will annotate. Although, as I say, eSIM has much more capabilities to do many advanced things to limit the hands-on session to a point where everyone can do. We will just do the annotate with the by default feature. So it will just not randomly, it will go like this to annotate. If you want to change the weight of annotation, you can do it. After click on annotation, whatever question mark was there, it will go. Now important thing.
Bharat,
Hello.
hello. You can
Yeah.
turn off your video.
Yeah, I will. Okay. Is my screen still visible?
Yes.
Yeah. So for now, as we know yesterday every one of you has simulated the example of half rectifier, but few of them only understand what happened with that. So what thing happen when whatever we design on that canvas, whatever we design on the canvas, now we will create a netlist and we'll link it with the eSIM. To do that, there are two things. If you're using eSIM version 2.5 that we are recommending just because it is latest release, and in case if someone's laptop is a bit older, has some older versions of OS like Windows 7 or earlier, then they might be using eSIM version 2.3. The both version need to have the netlist. For that, eSIM version 2.5, that is the latest one, you need to click on File, then Export and a netlist. It will show you the window like this, and this window will have a 4 multiple option. One is KiCad netlist, OrCAD PCB netlist, CAD Star, Spice. These are the proprietary softwares, but still it is there to just generate a netlist. What we will do, we will create one Spice netlist. So we need to click on Spice and then click on Export. After that, it will ask you to save that netlist. This time, be very careful to not rename anything, not to change any path. We will just say yes and we'll go forward. For now, this is done. Once we generated a netlist, we have to click on KiCad to ngSpice, this symbol. And then it will give you option of this. And for the halfway rectifier, we need to give these parameters for the simulation, for the two equation. First is transient analysis will perform. The start time will take 0. It will start from 0. We will do a step of 10 millisecond up to 100 millisecond. And for the sign, these are the parameter values that we will press and we'll see how the output will come. Once we click on before simulation, everyone need to make sure all of the tabs are filled. So all of the tabs means first is analysis, that we took transient, we add start, step and stop time. Now what we'll do, we will add these device modeling. See, source details, ngSpice model was not needed in this case. If in case your whatever design you have, which have to give some values, then the source detail you need to fill. Like in case a DC value, if you added a DC source, then you need to fill the value from the source detail. For now, this halfway rectifier, you just need to go on device modeling and you need to add a diode. As I said before, that schematic has one sine wave, one diode, resistor, and the ground. Only the diode is the device where we can change the model. Like, is it a normal diode, a power diode, or anything different? In eSIM, by default, we are giving you some 4-5 diodes. If you want to have your own diode, eSIM has that capability, and it gives you an option to create your own model. You can see when we click on add option on the left side, this blank window, this blank. This is a browse. It once you click on add, it will give these folders. From that folder, you will double click on diode, and then you will get this again 5 different types of diodes. For a normal use case, we will take a d.lib. It is a normal diode, and then we will add it, and then we will go forward for the simulation. To simulate it, we will click on a simulate option. This is the simulate option. Whenever I will see simulate, this option you should be looking for, and then you will click on this, and this will ask you for, do you want the ngSpice plots or not? If as yesterday, most of you have installed eSIM and has got this waveform, so you might be getting that right. So do you want ngSpice plot? We'll say yes, and then from the next, once you click yes, the ngSpice plots like this will appear. This is a sine wave, and this is the output wave. This is our aim for today. So, and for the Python plots, ngSpice plot, if we say yes, it will come with the Python plot. If we say no, then only Python plot will come. Now we have a Python plot as well. For the Python plot, you can see this in and out and the plot. Even you can check the multimeter readings of that particular nodes. So now we are good to go to the hands-on. Okay. So now I will just see if anyone has some doubts in the comment section. Slide is not visible. I hope everything is fine up to now. Deepak sir, everything is fine?
Yes, yes.
Slide. Okay, nice.
There is two hand
So
raised.
there is 200. Okay. Angelina, someone participant Angelina and Dr. Sadhana. If you have any particular question, you can ask. Okay. Is it any? Okay. So we will go to the hands-on now. So I hope everyone is with me for now. If everyone is with me, just type yes in the comment section so I could get to know that everyone is getting what exactly I explained. Yeah, as I see many of them are getting. So now the best thing that we will do a hands-on now. Okay. To do a hands-on, as we know, this is the eSIM logo that we need to double click. I already have a eSIM open, so we'll open eSIM. Whenever we open eSIM, this window will appear. This is the choose workspace. As everyone can see, the one who was not present yesterday, please see the recording and please follow the step that workspace should not have any space. Just click OK, and then this GUI will be pop up. On now you can see earlier it was PPT, but now it is an interactive hands-on. So be very much attentive, and I hope you will get a great learning from it to learn easy. For now, I kept some project here, but for the better understanding, I will create one fresh project and I will show how things get started from scratch. This is the welcome window. On the left side, you can see there is a new project. Now everyone know this is the dock area, this is the console area, this is the project explorer, this is the menu bar, this is the toolbar. So whenever I will say menu bar, you should focus on this part. First is a new project, open project, close project, change the workspace, help, and developer docs for the eSIM. Now I will create a new project. Let's name this project as test underscore half wave, and okay. You can name it anything. Now once it added, you can see at the bottom this line is added. I will double click on it to make sure the current project is selected. Now by default whenever project got created, it has a .prog file. But now we want to open a schematic. For that, this toolbar will help you. The first option from the toolbar is to open a schematic. I will click it there and I will wait to click it to open the schematic. Now you can see the area. The dialog box is asking me for a confirmation. Do you wish to create a new schematic? Just because the schematic is not exist, I will say yes. This is a canvas that is provided. You can even change the page layout from here to make your canvas big and small as per your application. Now all of our PPT things will come in the picture one by one. So I hope everyone is getting all things, and I will be repeating everything now. So for now, what will be the first thing to do? To add a component. To add a component, on the right side you can see the option called add a symbol that I took a screenshot and added in the PPT. I will click it here. It will take
Whereas you are not audible.
some time to load. And if you're sitting, then it might take a. I'm not audible. Hello, hello.
No, you are audible.
I'm audible, right?
Yeah, you're
Okay,
audible.
okay. Yeah. Yeah. As I said, uh, in case you are adding a symbols, you need to click on add symbol option. Once you click on that, it will take 20 to 30 seconds to show you the window to add a symbol. For now, it is taking a time just because the component library is much big enough. Now, I want to say a very important thing that everyone should take care of. One is ABD, analog, this, that. I already explained one thing. This library is categorized in two ways. One is eSim underscore. You can see there are many eSim underscore, and there are some other LT spice, this, that. So all others are having a footprint in that footprint for the PCBs. But now we are focusing on the simulation. So everyone need to use only component comes under eSIM underscore something, eSIM underscore analog devices, this, that. Or you can search it here. So first component that I will search is sign. And you can see eSIM underscore sources has this symbol. I will double click on it or I will click OK. Now you can see my mouse has this symbol called sign. I will place it in the canvas wherever I want. To move it, I will press M on my keyboard and I will get the access to move it. I will again press a left key on my mouse to place it. Now I will press escape button or you can click it somewhere to add the next component just because on the cursor if you can see there is same icon to add a symbol. So either you can press escape to leave it, press again this option to add a symbol. This time it won't take time. Now we will add a diode. To add a diode I will search eSIM underscore diode because I know to simulate something I need to use.
No, Parul?
Hello.
Yeah.
Yeah.
Show it again. Someone is asking.
Okay. Okay. So to add anything in the canvas, we need to click on this option called add a symbol. We will click on add a symbol option or we can press A and this time it will rapidly open a library because it is already loaded. Now I will repeat, there are categories of library like eSIM underscore library and a normal one. Whatever normal library you can see LT Spice, Mark, Port, this, that, it is for the PCB thing. And one we are focusing on is to simulate something. So now we are aware for simulation we will use eSIM underscore library. Now I will search eSIM underscore D to add a diode and I can see it is comes under eSIM devices. So I will press OK. Now I have again the diode in my hand. To rotate it I will press R. To press R this can be rotated. Okay. So I will keep it here. Now I will add the register. To add a register again, I will click it here or I can press A and I will search register. For register, I will say eSIM underscore R and this register will appear under the eSIM devices. If you just type register like this register will also work, but the above register won't work. So I recommend all of you to use eSIM underscore R as a register, which comes under eSIM devices. I will press OK in here. I want to rotate it. I will press R. I will place it here by clicking left click on my mouse. Now I will join it. To join, this is the wire. Add a wire. I will click it here, or you can press W on your keyboard wherever you want to start your wire. Now I will just wire everything. Once I have wire, I will just complete a circuit. Now circuit is complete, but we need to add a ground. So again, I need to leave this wire. One, I will press escape key on my keyboard, or I will press this cursor here. Okay. So now I want to add the ground. So I will add a symbol. Click on add a symbol. I will search eSIM underscore GND 2 and I will click OK. So eSIM underscore GND, this ground I got, I will add it here. You can see this dot. This is called, this is used to show the junction. As I explained, this is for not connect flag. This is a junction. So if I want to add junction here, I will press J. So it will add a junction like this. So as long as it is not needed here, what I will do, I will now add a plot because circuit is complete, but we need to plot because that is the aim of any simulation, right? To get to know what is the output, what is the outcome. So I will add plot V1 here. I will control C copy, control V to paste. I will again add a plot here. To search plot, I will press A and search PLOT underscore V1. That is the plot V1 that I am using. Once I add it, I will press W to wire it here. Now the plots are added. But as I say, this is not the sufficient thing. We need to state something. So now we will treat the left side as the input side. I will type as a I and in. I got a global label. I will again repeat how I got a global label. I will keep it here and then I will press W and I will wire it. You can see on the right hand side this one. Add a global label. This icon is used to add a global label. So I will click it here again. This time I will press say OUT for output and the shape you can change like input, output depends on it. Shape doesn't say that this is the input or output. Shape is just to identify. Now I will click OK. I will keep it here and to add a wire I will press W or I can take a wire from here. Just like this. You can see these three lines are there. That's why this junction dot is coming. If I just take a wire like parallel to here, it won't take a junction. If you want to take a junction, you need to press J. Now you can see the design is done, but some values are missing, like a register. Everyone please observe that R question mark means this is the number of the register. This is the first register, second register, how much register. And eSIM underscore R is the value for the register. So on this line, I will click double click. It give me access to write a value. I will press 1K and I will say OK. Sometimes you might double click on this register icon and it will give a big something like this. Here also in the value section, you will add a value. This is just for a reference. And the other are footprints that are still enabled, but we didn't add it. If we add something, it will reflect. You can either give a value from double click on the eSIM underscore R or double click over here, or you can simply press V on your keyboard. It will give the same thing. Now for the sign, as everyone knows, sign has many things to be added. So what we'll do, we won't add it here. To just, I will show you how to add, if we miss to add some data on the main schematic, where to add it. I will show that. And for the diode, this is the eSIM underscore diode. We will add a diode library later. Now this is done. I will control S to save, or I will go to file. I will press save. After saving it, I need to create a netlist. To create a netlist, everyone please observe, on the left side there is a file, export, and the netlist. This netlist window on the fourth tab, that is a spice. We will click export netlist. Here I will not make any changes to the name, to the path, or anything. I will just save it. It will ask me to annotate, just because all of the component like U question mark, R question marks are not annotated. So you can see these are the order, like this vertical order, horizontal order, what you want. You just say annotate. No need to do anything here. Just annotate. Once you annotate, you can see this plot has U1, this plot has U2. It means it has annotated like this, like a S shape, symmetrical S shape. For register also R1. I will again save it. We already created netlist. We will minimize this. So for everyone, dear participant, this is a black window for the command line of the eSIM. This is the eSIM GUI, and this is the schematic. Schematic is done. I save it. I created a netlist. I have minimized that. Now in the main eSIM GUI, I will see whether my current project is still selected. Yes, it is selected. And then schematic was called. If in case you accidentally click on any other project, make sure to double click on the current project that you are working on, and then only click on KiCad to Spice. I repeat, just after the schematic, save it, convert netlist, take the export netlist, then click on KiCad to ngSpice if this is still selected. If you accidentally select something else, then double click on it and press KiCad to ngSpice. Now you can see this dock area, the welcome window. You can see welcome and this one. It is changed to a window called analysis. I kept transient and I will add values like I will take 0, 10 and 100, but all in millisecond to make the simulation quicker. Now source detail. As I said, why the source detail box is
So,
appear.
well,
Hello?
yeah,
Yeah,
people are saying you are so fast.
I'm so fast.
Yeah,
Okay,
kind of.
okay, okay, okay. I will repeat it again with a slow speed. We done one thing. We done with the schematic. After done with the schematic, I save it by clicking on File and Save. Done with schematic, done with saving, we'll do export, netlist, and spice. Once we exported, we will save it as it is. Then we will just minimize this. Once we minimize everything, I will off it here. Once we minimize everything, this is the main eSIM GUI where the project is available, and we will click on the KiCad to ngSpice option. What it will do, it will take our exported netlist and give us access to perform a simulation, perform a different types of simulation. So I will click here, KiCad to ngSpice, and the dock area will be now a netlist dock area where we can see whatever we want to do. So for the analysis, there are three type of analysis. For now, I'm taking a transient analysis. The start time I will keep at a 0. I will select here second and I will make it a millisecond. For step time, I will keep it 10 and I will add a same 10 millisecond. And for the stop time, we will run it for 100 milliseconds. I hope everyone is with me here. After that, this is the analysis. We'll go to the next step, that is the source details. In the source details, you can see source detail for what? Source detail for the sign. Why only sign? Just because in our schematic, there is only one source. If there are multiple sources like a DC, sine or pulse, something else, everything will appear. But only if we didn't add the values within the canvas. You can see for the register, I added the value because register is not a source. That's why I added the value here. In case of source, if I added value here, then in our eSIM main GUI, this will not come. To make the changes, we will keep it as it is in the canvas, and you can see this is appearing. Why? Just because I'm using a default sign. Now, what source values we will add? We will do a, we'll start with offset 0. We'll take an amplitude of 20 volts, the frequency of 50, delay time we won't keep anything, and no damping factor. Now, source detail has done. Let's see ngSpice model. As I say, in case your canvas has any ngSpice model, then only it will appear. Most of the time, whenever we do mixed signal simulation, that time ADC we used, and there you can tune it. Now, device modeling. 1, 2, 3, 4. 4 is device modeling. Whatever devices are there present in the canvas will be listing here, and it will eSIM will ask you to add the particular library for that particular component. Component means particular diode. In our case, we can see it has only one eSIM underscore diode. So that here also eSIM underscore diode is appeared. We will click on add option here to add the diode, add the library for the diode. Once I click here, this is the window to browse it. So for now we have multiple components, but we know this is a diode. So we will open a diode folder on the top, double click on it. Again, there are the list of diodes. As I say, it is a normal half-wave rectifier. We can take a normal diode. If we are considering as a power electronics application of a half-wave rectifier, then we will take a power diode. For now, I will take a normal diode. I will click open. Now you can see the path has changed from empty to d.lib. Where you will get this library, by default it will browse it. If you have failed to browse it, then it will be under your local disk C, then FOSSI folder, then eSIM folder, then library, then device model library, then there is a diode folder, and then d.lib. Anyways, whenever you add it, it will automatically browse to give you the different folders to add a library. Now we will see next tab, it's sub-circuit. We already know this this canvas, the circuit is we are taking is a normal one. So it don't have any sub-circuit and it don't have any microcontroller. Everyone need to go through all of these steps one by one to make sure everything you have filled. Sometimes in the ngSpice model, there will be some listing of component, but all of them have by default value. So there you no need to put anything. For the source details, you can see there is nowhere it is written that by default some value is taken. That's why we put values. In the ngSpice, in the here you will get a bracket. In that braces, it will mention by default these values will be taken, and if you want to change, then eSIM give you option. I repeat once, we done with schematic. We can click at to ngSpice. We did. We got this dock area where we done transient. We added the values. We added the source details. We added a device model, and now I will click on convert button. Once I click on convert button, I got a dialog box that KiCad to ngSpice conversion completed successfully, and I will press OK. Now everything is done, but you can see still nothing is happening here. For that, you need to press right click and refresh the project. You just need to right click and refresh. Even though if you didn't refresh, still it will work. To just for a mind piece, we are refreshing. Now let's come on the toolbar. At the beginning of my PPT, I said we are following three major steps. One is open schematic, convert KiCad to ngSpice, and simulate. Two of them we explored bit well. Now we will click on the simulate option. Once we click it here, it gives me a dialog box to say yes or no. Do you want ngSpice plots? For my preference, I like ngSpice plots. So I press yes. Once I say yes, simulation will carry it out in the backend, and this ngSpice plot will be appear. On the backside you can see this white canvas in the dock area. It's the Python plot. Let me explain. You can drag it from this toolbar. This white portion is to drag it anywhere you want, and if you want to zoom any particular portion on the mouse, on the right key of your mouse, you need to keep it pressed, and you will get this option, the dotted square. You just need to drag, and wherever you want to do, like up to here, if you want to do, then keep it like this and release your right hand, right mouse key. Then you can see this is a new Python plot appear. Whatever you want to zoom, you can zoom like this. But the now thing comes, this is the ngSpice plot, but we will still want to see the Python plot. So what we will do? We can either close it or minimize it. So for my case, I'm done with the ngSpice, so I will close it one by one. And as I said, this is the ngSpice terminal. If you want to plot something like v plot v in, and you press enter, then this terminal give you access to plot. So accidentally if you close something, you can anyways use the ngSpice terminal to operate the ngSpice more efficient way. Now I will quit the ngSpice and I will show how the dock area is now looking. This is the eSim dock area where we now supposed to look for the waveforms for the outputs. You can clearly see on the right hand side there is in and out. So I will click on in and I will click on plot. This is the same output that we got, but the difference is this is being done and processed by the Python plotting feature of eSim without a ngSpice integration. And this is the out, and I will again plot it. So you can see it is overlapped, so we can say that the output is correct. If you want to do same thing in the ngSpice, you can do with the help of terminal. If you want to look for the multimeter readings of the same or the RMS value, you will click here once, and for the both node in and node out, we can get the RMS value for it. I will close this. So we are very close to our lunch break at 1. I have almost 1 minute to conclude it. So I will conclude it as a way we done 3 major steps. First was to create a schematic, to create a KiCad to ngSpice, to do a KiCad to ngSpice, to simulate. So I will just quickly go to my PPT to make you aware of the steps. So as everyone can see, this is the same important step that we did. One is schematic, KiCad, and simulate. We're done with the schematic creation. We're done with the exporting it. So let's go one by one. We open. This time I will be very quick to recap everything. Open schematic, then KiCad to ngSpice, and then simulate. And which library we used? We used the eSim underscore library just because it has a spice model at the backend. Which library we used here? These are the 5 major components that we used for the simulation. And now the global label that we used is input and output. And after that, the steps were open schematic from this icon. To draw the schematic like this, we added register, diode, sine wave, ground, plots, and global labels in that. Just after this, we annotate everything with this option. After the annotation, we generated the netlist successfully. For that, we click on File, Export, Netlist, and particularly Spice Netlist. Once we're done with the Spice Netlist, we again went back to the main eSim GUI, and then we click on Keycat to ngSpice, where we choose which analysis should be done. So which analysis we done? We done a transient analysis. For transient analysis, we kept the start step and stop time as below and the parameter of the sine source like this. After that, we added a library for the diode, which is very important. How we added that? We click on device modeling and we add it like a using our basic browse feature of our Windows. We browse it, diode folder, we browse the diode d.lib. Then we click on simulate where we got a dialog box for yes and no for the ngSpice. We said yes, and ngSpice plots appear like this with its terminal. After the ngSpice plot, we also got the Python plot like this, and these Python plots was the end of our hands-on. So I will quickly come to the our meeting link to see as everyone is able to. Yes, please share the PPT also to grab easily from it. Yes, for sure I'm sharing the PPT here. And also let me share the codes like I am adding a link here. Okay. Yeah, thank you so much. So here I added a Google Drive link. I will show you what is consist of. In this Google Drive, I kept a half-hour.test project file. In case any of you didn't able to get the output, they can take a reference from the circuit. You can just download it and you can use. And this flat top I will be discussing in the post lunch after the lecture of Professor Indrajit sir. And that will be that lecture will be very nice. He is a very nice person and he has also been our faculty partner, and he is currently doing a PhD researcher at the University of Exeter at United Kingdom. So the afternoon, like after the lunch, this session will be very nice. That Professor Indrajit will be covering most of the analytic part in the technical aspects, and then I will show you the hands-on, and then I will be giving time to you all of you to do the hands-on by your own. So now I will open my camera again. Okay. 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 I hope I'm still visible to everyone. Hello?
You're still present.
I'm still presenting, right? Yeah. So what I wanna show, that's okay. I will just stop my presenting. Yeah. So for everyone, this PDF, like PPT, everyone's on, right? So I will create a public version of the PPT so that everyone can see parallelly. Create a public view link that I created. Okay, I copied as well. So I'm adding it here. Yeah, I shared a PPT in the comment section, and for all participants, I request to go up to the flat top, not to cover the flat top example, just because I'll be explaining that in the next half, and I'll be showing uh, that good example after that session. And if you wish to do, then yeah, obviously software is open for all, for all open source people and for everyone. So yeah, so we can conclude it here. That we are very near to our lunch, and I hope everyone is here from morning. Shanti, the attendance is done.
Yeah, it's
Yeah. So if okay, when in digital design extension, yeah, we will be having a digital design today at evening session. Actually, today's session is divided into three parts, just because our one of the speaker, Steve Hoover, who is the founder of Redwood EDA and who is currently at the USA, and that's why we kept that the time slot. Little convenient to all of us, like for little for us, little for him. So its session is at around 7:30. So today in afternoon, Shanti, please share the attendance link in the comment section once again. So today what we will do, once after the in afternoon session, we will do that particular session. One is the lecture session, technical session, and one hands-on, and then we will conclude so that everyone will get a rest. And I expect all of you to come for the beautiful lecture from the Steve, who is the our faculty partner as well. He's the founder of Redwood EDA, who is a startup focused on LLM assisted digital circuit design using a next generation modeling techniques. And he will be a best person to explain, and Shanti will be providing you a digital simulation in that session. Uh, if everyone is enjoyed the session, they can put a thumb, or they can put a just yes in that comment section, so that I could get to know everyone got to know at least the flow. Uh, I can see few of them has said yes, they got it. And I encourage everyone to use eSIM with this example, just because yesterday for the installation we took the same example, just because to make you familiar with the eSIM, and I hope everyone is familiar. Yesterday we just simulated that by using pre existing example, but today we actually made it possible, made it run, and this session is recorded on YouTube. So in case someone missed some part, and they can follow it, and the PPT session PPT link also I share. So I hope everyone will use it. And for the code source, I again add it in the comment section. The PPT link, I will share it again. Okay. One is the drive folder where that file is present, and one is the, yeah, thank you so much. Thank you so much. In case you have any doubts, anything is there, you can anyways reach out to me and our team. This is our email. This is our eSIM contact dash eSIM at the rate possibility. So Sumanto sir, are you here? Sumanto sir. Okay. Deepak sir, you can start that afternoon lunch break wala part. Like share that.
Next session will start what time?
Next session, let me check. At 2 o'clock. So we will expect everyone will come up to 2:15. Same like yesterday.
Okay, okay.
Yeah. So thank you everyone for joining us. I hope everyone will come at 2, and we will have a very beautiful session from Professor Indrajit. and then we will do a hands-on. And then I will be there only for solving all of your queries. We'll do some breakout session, and I will solve every one of your doubts and whatever it is. And then I will show you very beautiful example of a flat top sampling that I shared in that PPT. You can take a look into that, but still, stay tuned. Have a good lunch, and we'll meet soon. Yeah, thank you so much to all participants to being here. Yeah, you can either be in the meeting, or if you want to leave the meeting and wanna join it again, that is also possible. Yeah, Deepak sir, you can present it. Yeah. Okay then. Thank you everyone for joining us. Please be there up to 2:15 so that try to be early if possible at 2, and Professor Indrajit will be continuing from 2:15. Yeah. Hello everyone. I'm audible?
Yes, sir.
Okay. Indrajit sir, I'm audible to you as well?
Yes, yes. Hello.
Yeah. Actually, Sumanto sir is little not available for now. So I will be introducing you and we will start the session in maybe 5 minutes. So we'll wait for 5 minutes to get participant in. Most of them are there. Actually.
Yeah, sure. No problem.
Yeah, yeah.
So Varad, I have joined from two devices.
Okay.
One is my laptop for the audio and the
Mhm.
video, and one is iPad because I have to write live. So will it be possible for me to use both?
Yeah, yeah. It is possible.
Okay,
For now, we have make you as a
You can try
co-host.
sharing the screen. This.
Yeah, yeah. Both of the IDs we make as a co-host, so you can have access.
okay, okay.
Yeah,
Thank you. And
yeah.
do I have to turn on my camera while explaining also? Because I mean, whatever you'll require.
As per your convenience, if you're okay to write and present, that is fine. But as per your
Okay.
convenience,
Okay, fine.
yeah,
Can I share my screen and test before we start?
yeah, yeah, fine. Yes, yes.
Are the slides visible?
Yeah,
Okay. Let me check if I can write something. Okay, yeah.
yes. It is
And
absolutely
audio
nice.
and audio is fine.
Yeah, audio is also nice. Okay.
Okay. So I keep it on for some time, and then while I start, then I can.
Yeah, yeah,
Okay. Thank you.
yeah. Okay, we are good to go. I hope I'm audible to everyone.
Yes, sir.
Yeah. So, hello everyone. Again, warm welcome you all to the afternoon session of Faculty Development Program for CIIT Bombay. So, in this half, we have our speaker, Professor Indrajit Singh sir. He's a researcher at University of Exeter at United Kingdom and also a former assistant professor at KJ Somaya College of Engineering. He's with FOSI team from very long, and he's also one of the faculty partner of us. He has over 12 years of experience in academia. He served as a professor in electronics and engineering, and also has expertise in analog electronics, VLSI design, integrated circuit and technology. And he's one of the finest professors that contrib- actively contribute to the FOSI project. So I just warmly welcome Professor Indrajit sir to the faculty development program that we organize today. So over to you, sir.
Yeah, thank you, Varad. Can I share my screen again? Hello, everyone. May I start?
Yes, yes, yes.
All right. Okay, so hello, everyone. Today we are going to cover the following topics in brief. I have only 1 hour with me, so the time is limited. So we'll start with some applications of diode. Then we'll go through discrete BJT amplifier and differential amplifier. Then related to the VLSI design, the current mirror topic is very important. And we'll conclude the session by discussing operational transconductance amplifier, that is OTA. Okay, so let us start. Um, I thought of starting with the very simplest diode application, that is using PN junction diodes. So it's important that whenever we start with the diode, it's important that we model the diode correctly into the simulators. So as we all know, the diode is a nonlinear device. So this is a nonlinear device. Now, to correctly model the diode, we use diode models. We all know that the diode characteristics is exponential in nature. This is the diode voltage, diode current. Now, the expression is given as the saturation current into exponential of diode voltage. Now, this represents that the diode is a nonlinear device. So we can model the diode as follows. So one of the diode model can be exponential model. So this is quite an accurate model provided we know the value of IS. So IS should be known to us. If we don't know the value of IS, then it will be very difficult to evaluate the diode current for the given diode voltage. And let's consider the second model. The second model is linear model, or we call it piecewise linear model. So here, let me draw the characteristics and explain it to you. So the same diode characteristics, if I represent it as a dotted line. So in the piecewise linear model, we consider a tangent over this, and so this approximated straight line, this is a straight line, this approximated straight line is my piecewise linear model. So your diode is represented closely in terms of your exponential model. In this case, it will be a straight line. And the slope of the straight line is your resistance. So this will be a slope over here. So the resistance of the slope will be R, let's say. It will be delta VD upon delta ID. Now, this model is also useful for if we know the value of this R on resistance, and we know that whenever the diode is conducting, its resistance is quite less. Now we have, let's consider a different model now. So next we consider constant voltage model. So in case of constant voltage model, what we consider is that the diode will be off till a constant on voltage. We know that the diode turn on voltage is around VD on is around 0.6 to 0.7 for the silicon diodes. So what we consider is we consider that this diode will be off if my applied voltage is less than VD on, and this VD on is around 0.6 to 0.7, and it will be on if my applied voltage VD is greater than VD on. So that is what this constant voltage model considers. So basically what are we doing is we are representing the diode over here in a constant voltage model as a voltage source with an ideal diode. This is an ideal diode. All right. So we consider this. We represent the diode, current flowing through the diode, and voltage applied with a battery, which is your VD on. All right. So these are the components of your constant voltage model. Now the next model is an approximation of constant voltage model, which is your ideal diode model. So your ideal diode model will be, so this is the fourth one. So in case of ideal diode model, we consider it's a special case of constant voltage model. When we consider VD on is to be approximately 0. So in various applications of diode, let's say in rectifier, the applied input voltage is quite high compared to the diode on voltage. So 0.7 is quite less as compared to input. So in some cases, for quick analysis, even a simpler model than a constant voltage model is considered, and that is your ideal diode model. So in case of ideal diode model, whenever the voltage is positive, the applied voltage is positive, the diode turns on. So here it is. And whenever the voltage is negative, the diode turns off. It's not a very good approximation, but it's like behaving like a very good quick calculation. We can analyze the complex circuit and we can apply the ideal diode model. So this essentially says that the diode D passes positive voltages, and it blocks all negative voltages. All right. Now let's see an example where this can be used. Any doubt anywhere? Anyone? Okay. Yeah. So let's see an example where why studying this different diode models is important. Let's say if you have a circuit consisting of a diode and a battery. Let's say that battery is VB and diode is D1. Let's say the voltage across the diode is VD1. This resistance is R1, and because of this applied potential VB, current flows to the diode. Now in this case, I want to find the current. Now if I use a exact model, that is my exponential model, I need to know the value of Is. And still, since it's an exponential model, the relationship between VD and ID won't be linear. So it's very difficult. You have to iterate a lot. So what if we use a constant voltage model over here? So in this case, if we use a constant voltage model, the same circuit will look like this. So diode will be represented, if it is on, we assume it to be on, so it's considered as a short circuit. So this will be VD on. So we have replaced the diode with this model. So this is considering the constant voltage model. Now, if I want to find the current Ix, we can simply apply the KVL, and it will be minus VD is equal to Ix times R1 plus VD on. So if I want to find current Ix in a circuit which involves diode, it's very simple calculation. It's VB minus VD on, provided you know the value of VD on, divided by R1. So this simplifies our analysis. All right. Any other query? Can I proceed ahead?
Sir, there is one thing. The video
Yeah.
can we minimize that video that is going on the iPad?
Oh, okay, okay. Yeah, yeah.
Yeah,
Now it's fine.
yeah. And one participant Harsha is saying, sorry to interrupt, but can you please repeat this quickly?
Okay. Yeah. So we have a diode. We are starting with the diode. It has exponential characteristics, and we modeled the diode in order for the simulator to work. So we have different types of models, diode models. First is the exponential model. In exponential model, it represents the exact characteristics of a diode, which is exponential in nature. In piecewise linear model, the diode, it behaves as, let me just write it again over here. So the equivalent circuit of the diode in case of piecewise linear model will look like this. Where should I write it? Over here, left hand side. So in case of this is the representation of a diode. This is R on or RP resistance, which I talked about, and this is my VD on, the voltage. So we modeled the diode such that it will have an on-state resistance and it will have its own voltage drop. Then we went to the constant voltage model. In constant voltage model, we approximated the exponential characteristics. So this was the constant voltage model. So we approximated this exponential characteristics because this voltage is not very much changing for a large change in the current. So this voltage might change from zero point 0.5 to around, let's say, zero point 0.7, right? So it's a good approximation basically. So in this case, we consider that all the voltages, that is any VD, applied voltage is greater than VD on, then the diode is on. If else, if applied voltage VD is less than VD on, then the diode is off. And a special case of constant voltage model is ideal diode model. In this case, we consider VD on to be 0. This is for quick analysis of the circuits. So one of the applications of using the diode model is in a circuit which contains a diode with a resistor and a supply. So in this case, we can easily calculate the current flowing through the diode without going into the realistic expression, because in this case, the realistic expression of the current flowing through the diode is different. So yeah. Any queries further?
No, he's saying thank you so much.
Yeah. Okay. Now let's come to the application part. In this case, I have one of the applications of diode will be the clipper circuits. So clipper circuits are those circuits which clip a part of the input waveform. In this case, it is clipping of the let me show it to you. In this case, it's clipping a part of the positive half cycle of the input. So this is a positive clipper. And we can easily use a simulation tool to verify its timing characteristics, that is input output characteristics, and this is my voltage transfer characteristics. So voltage transfer characteristics is between the input voltage and output voltage. How does the diode behave? So in this case, as you can quickly see over here, when the diode is on, it will behave as a short circuit. So let me redraw the circuit diagram over here. So it will behave as if we have a constant voltage over here around 0.7. Let's consider, and this is my output. Let's say the diode is on. So during the positive half cycle, if we consider the diode is on after V in is greater than V on, of course R1 resistance has to be considered. And in that case, my output is approximately equal to VD on, which is zero point 0.7, which is what is visible over here in this diagram, as you can see. During the positive half cycle, the voltage across the diode remains at zero point 0.7. And during the negative half cycle, the diode is off. It will behave as open circuit. So when it behaves as an open circuit, the current flowing through the circuit will be almost negligible. So there will be no voltage drop across the resistor. So my output will be same as my input in a negative half cycle. So that's what the characteristics looks like in a negative half cycle. And the same is represented in terms of the voltage transfer characteristics. All right. So what is an application of such a circuit? These circuits are used in Bluetooth receivers to limit the amount of voltage which is coming. Or it can be also, so the similar circuit can be used for this as a half wave rectifier. So it has different functioning. It is also called as a limiter because it limits the output voltage. All right. And here we have another application of the diode. So can anyone tell me what this circuit is? So we have a triangular waveform. It's been shifted up. So what is this circuit called as? Can any of the participants let me know?
There are few answers. So they are saying clamper or level shifter. Someone is
Yes,
saying
it's
negative clamper.
yes, exactly. So it's absolutely correct. So it's a clamper or a level shifter. So it doesn't change the input waveform. It just the shift the DC level of the input waveform up. So in this case, it is shifting down DC level of a circuit. So in this case, it involves a capacitor, which is a storage of charges, which involves storage of charges, and we have a silicon diode, and we can also consider a constant voltage model in this case to analyze the circuit. So I'm not going in details because we have a limited time, but these are the few applications of diode. Then some more applications are voltage doubler. So we can simulate all these applications quickly in eSim. We can, I mean, if we are presenting it to explaining it to the students, then we can use the help of simulation tools like this and bridge the gap between the theory and the practicality. So this is the application of diode models, and diode applications. Does anyone has any query before I move on? Okay. Can I go to the next slide?
Yeah, we can.
Okay. Now let's consider some BJT, the discrete BJT circuit. So why discrete? Because we are going to use an amplifier which can be fitted on all the components can be mounted on the breadboard, and it involves a lot of resistors. And in integrated circuit in VLSI design, we really don't use resistors. So why do we study BJT circuits? To develop the fundamental knowledge, the concept of um, amplification. So in case of any amplifier, so let's say if we have an amplifier block, what are the fundamental requirement for an amplifier? So of course, it should amplify the signal. So it should have its high gain. So one of the requirement is its gain should be high. Second requirement is we have to check its input and output impedance, because we don't only use single stage amplifiers, we worry about the interconnection between the amplifiers. And the third and most important is linearity. So the output should be linear with respect to input. And in this case, the active device which has been used to build amplifiers in this case is BJT. So in this case, BJT is a current control device which is amplifying a small time varying signal. So why we consider it amplifies a small time varying signal? So in this amplifier, the V in is supposed to be very, very small. So usually it's in millivolt level. Why it should be in the millivolt level? The reason being, if you increase the value of V in it, your BJT will saturate. So that's why the small time varying signal is very, very important. And in this linear range, in this small input range, only the device will behave as linear. The BJT will behave as in the linear region. Okay. So BJT can act as a voltage dependent current source. It converts. So BJT converts voltage at its terminals. So this is your BJT, discrete BJT. So it converts VBE to a current, which is IC at the output. All right. Now, when we model this BJT in terms of any circuit, so lots of discrete, the analog circuits uses BJT and MOSFETs. So when we model this device, we don't represent, so when we put this in a simulator, just like eSim or any other open source tools, uh, we don't just drag the symbol, we drag its in model also. So we have something called as small signal model or hybrid pi model of BJT. I'm considering NP and BJT in this case for simplicity. Similarly, we can have PNP BJT. So we consider the three terminals, the base, the collector, and the emitter. So a simplistic model of a hybrid pi model will be containing a resistance between base and emitter representing variations in the base emitter voltage. So this is called as R pi, and the voltage across it is V pi. And the if we have a voltage dependent current source represented by Gm into V pi. So Gm into V pi will represent the variations in the collector current. And finally, we have some output slope in the characteristics. So we have Ro, which represents the small signal output resistance. And we all know these parameters, it has its own formulas to solve. So this depends upon IBQ upon VT, thermal voltage. VT is around, I think, 26 millivolt. Yeah. And RO, it's early voltage upon ICQ. And GM, which is the BJT transconductance, it is ICQ upon VT. So if we want to solve a analog circuit involving BJT amplifiers, we have to replace this. This is again a non-linear device. So by keeping the signal very, very small, so what are we doing this non-linear signal, we make an attempt to linearize this non-linear device in order to evaluate its properties. So the linearity factor is extremely important. So these all represent small variations in base emitter voltage, small variations in collector current, or small variations in output resistance, the small signal model. Okay, any query over here?
No queries for now.
Okay, okay. Thank you. Sorry for inconvenience. I have less time to prepare, so I've taken some of the slides from the lecture material which I used. So this is what I was talking about. The common emitter amplifier. We can build any amplifier using BJT, but it will involve all the resistors. But why do we study still? Because we know that it's a good start. When we study amplifiers, it's very easy to use resistors for biasing the transistor. So all these resistors, R1, R2, are biasing resistors. We are biasing the BJT to operate in its active region. Okay, so it's all these biasing are used so that the BJT wakes up with the help of power supply. So we have your DC, which will power the amplifier, and this is my small signal AC signal. And this is contains, so we use capacitors to block AC, to block the DC and allow AC to go through. So this contains AC, and all the CE capacitor is used to bypass the AC to the ground. So as you can see, a simple amplifier, it involves, and this RSEG is my input source resistance. Okay, so it is very less RSEG. And so we use, in order to amplify, make the BJT use as an amplifier, we require 4 resistors. And whereas in integrated circuit, we don't use resistors because it eats up the space of 100 transistors, let's say. So it's very heavily, it's heavy space constraint in case of integrated circuits. So this is a very famous circuit of common emitter amplifier, wherein the gain, the voltage gain depends upon minus GM times RC parallel to RL. I mean, it also have small RO. So if you consider that, RO, RC parallel to RL. So in this case, if we want to change the gain, we can either change the gain by changing GM, and or by GM means we can change the biasing current, that is ICQ, or by changing the resistor values. Now, resistor values we cannot increase or decrease because we normally don't use resistors. So we'll come back to that. And just a quick comparison about different types of common emitter, common base, and common collector amplifiers. So they have different features. For example, wherever we require a very high gain, we go for common emitter or common base, whereas common collector is mostly used as a buffer, so its voltage gain is 1. But wherever we require a very high input impedance, then we have a common collector configuration. And if we require a low input impedance, then we go for a common base. And if we require a very low output impedance, so we go for a common collector. And they have its different applications. For example, common emitter amplifier is usually mostly used as as an amplifier. Common base is used basically for non-inverting amplifiers, and common collector is basically used wherever we require buffers, voltage buffer with a voltage gain 1 and very high impedance and very low output impedance. All right. Anyone has any query in this, or shall I move ahead?
Yeah, as I
Okay.
said, no queries.
Okay. Thank you. Now next, when we go for amplifiers, we know that the amplifier will not work at all frequencies, because we know that at lower frequencies the gain drops, and higher frequency the gain also drops. So typically, if we plot the amplifier frequency response, it will usually end up like this. So we have a lower cutoff frequency, we have a higher cutoff frequency, and this is my frequencies, and this is my voltage gain in dB. And the bandwidth will be the range of frequencies over which the gain of the amplifier remains constant. So the gain of the amplifier remains constant between FH and FL, and that is my bandwidth. So what will affect the bandwidth? I mean, we consider the frequency response, and many of the circuits which we use today all around are high speed circuits. High speed circuits are everywhere. For example, Wi-Fi, it operates around 2.4 gigahertz or 5 gigahertz. Then Bluetooth also operates at a similar frequency. Your GPS operates at around 1.5 gigahertz. Your automotive radars works at around 26 to 75 gigahertz, and microprocessors used in the laptops uses around 4 to 5 gigahertz. So we have lots of circuit which runs at high speed. To be able to run a given circuit at such high speed, we have to design it properly. We'll see that there are many limitations which comes into picture. So we should have exact understanding of what is limiting the speed, what is limiting the maximum frequency that circuit can take. So we have to ask this question: what is limiting the max operating frequency of the circuit? And that is the motivation in studying uh, the frequency response of amplifier. So it determines the speed limitation. So let's say if you have an amplifier, and we are applying a time step input like this, it's V in 0 to V1 it goes, and at the output it's supposed to amplify, but it's giving the output like this. So we have a this is like a fast response. So it should amplify, but it should react very fast to the input changes. So the output response to the input changes quickly to the input changes. That's a very, very good amplifier. So this is like a fast amplifier. So this is my amplifier. And in case if it is a very slow amplifier, it cannot keep up with the speed, then its response looks something like this. It's a sluggish response. So this is like we can call it a slow amplifier. So we have to understand what is the culprit which is responsible for reducing the speed. So in this case, if we analyze a very simple circuit, a very simple RC circuit, it's basically a high pass filter. So basically when we observe its output characteristics, its output equation, can anyone tell me what will be the output expression of this? V out? It will be given by V1 times 1 minus e raised to minus t upon tau, where our tau is the time constant, R1 C1. So if we apply a input like this, a step input, its output will behave like this in exponentially nature. So this is my V out. So V out cannot respond quickly to the input changes if tau is excessively long. Okay, so to improve the speed of this high pass filter, what do we do? What we have to do to improve the speed? We have to minimize R1 C1. And which is not always the case. It's not always the solution to minimize the value of resistors or capacitors. So basically, if we go ahead, we see that the capacitor is the main culprit, which will limit the circuit operation at higher frequencies. And then frequency domain analysis will help us to analyze, let's say if this is my frequency response. So this represents, what does represent? It represents a slow sinusoid, a low frequency signal. And in this case, it represents a high frequency signal. So what does this high pass filter tell us? So this is a high frequency signal. If you operate at lower frequency, or in this case the cutoff frequency is 1.59, if you operate this circuit at a frequency higher than 1.59 kilohertz, it will start to reduce its gain. So this is one simple example explaining the concept that why the circuit behaves, uh, you know, why the circuit is attenuating at the input signal at higher frequencies. So we have to consider, in this case, the bandwidth of the circuit is 1.59 kilohertz. So in very complex circuits where we have to design circuits, like in case of Wi-Fi, Bluetooth, GPS, we have to see to it that the circuit works well at these particular high frequencies. Okay. Any query here? All right. So as you can see, there are internal capacitance which are associated, which are responsible for fall of frequency fall of gain at higher frequency. So I've again talked about this. So this is my frequency response, frequency versus gain in dB. So in this case, my fall of gain in low frequency is dependent upon external capacitors like CC1, CC2, and CE, bypass capacitor. Whereas fall of gain at high frequency depends upon intrinsic capacitors, or capacitors which are inherent inside the BJT. So these are CBC, CBE, or CCB, just to name a few, and few wiring or stray capacitances. Then we exploit the Miller theorem to understand, and we build a hybrid pi model. I'm not going to details, and we get a different cutoff frequency. So for a different, each component of capacitor will give rise to different sets of these things. As I hope you're following what I'm saying. And in this case, we calculate. Why do we do this analysis? To calculate at what frequencies does this amplifier operate at safely, at what frequencies the gain is constant, and at what higher frequency it will limit itself. That is, this is the maximum I can go. So this fh can be in megahertz or can be its gigahertz. All right, can I go ahead?
Yeah.
Okay. Yeah, this is what I was talking about. I'm not going into details about this. So, I mean, we replace, in this case, we consider the MOSFET as an example. So simply replace the BJT with the MOSFET, and all the fundamental concepts remains the same. Only thing difference here is that we represent the small signal model differently. In this case, in case of a MOSFET, in the hybrid pi model of the MOSFET, we don't have anything connected between gate and source because the gate current is zero. Because MOSFET has very high input impedance, so it will have very high Zin. And we just replace the hybrid pi model and we do the analysis and find out the higher cutoff frequency, FHI, FHO, and the lower cutoff frequency, and determine uh, the bandwidth of the system. Yeah, this was just to give an example of how we do the analysis. All right. And then we have different types of multi-stage amplifiers. So we have cascade amplifiers. So cascade amplifier involving cascading two different stages, that is common emitter, common emitter. Simple example will be common emitter, common emitter, and oh, sorry, cascade. And then we have cascode. So cascode amplifier will represent common emitter, common base, and in terms of MOSFET, it can be common source, common gate. So the advantages is that in cascode, two transistors are stacked, sharing the same current part. And in case of cascade, multiple stages are connected in series. So there is amplification of multiplication of gain of individual stages in case of cascading. But cascading will be overall gain in cascading will be, let me go over here. Overall, we want very high gain. So overall, we have AV very, very high, multiplication of individual stages. Whereas in case of cascode, its job is to increase the output impedance or bandwidth. So here we are looking to increase the bandwidth. It reduces the Miller effect, kind of. And yeah, the number of stages will be in cascade. It can be more than two. In cascade is generally two stages. It's basically in cascade we use for gain boosting, and in case of cascade it's basically used in current sources or high bandwidth or op-amp output stages. All right, and then also we have Darlington pair. In Darlington pair amplifiers, we have a very high current gain. So there are some applications where we require a very tremendously high current gain. So it multiplies the current gain of two transistors connected. Okay. Any query in this? So we can simulate these circuits in eSIM and evaluate its performance and cross-check its DC analysis. So we have three types, different types of analysis. DC analysis, we find the biasing points of all the currents and voltages in the circuit. Then we go for AC analysis. In AC analysis, we extract the voltage gain, the input resistance, and the output resistance or impedance of the circuit. And then we go for frequency analysis to check the bandwidth of the system, the overall operating limit, the speed of the system. All right. Any query in here? Okay. And now we go for a differential amplifier. So a differential amplifier has a very high CMRR. So a single stage amplifier is vulnerable to noise. So in this case, even if the noise enters both the sides, it cancels out at the output. So your noise cancellation is very good in case of differential amplifier. It's especially useful in case where we deal with microvolt level input signals or millivolt level input signals, and these are like ECG signals, biomedical signals basically. Okay, so in this case the differential amplifier comes into picture, and already we can look, it's an amplifier without any if we have an excellent noise rejection and a DC coupling in case of single stage amplifier. So if we compare single stage, and I'm writing it short form as DFAM, so its CMRR, it's poor. the ability to reject the noise signal, and here it is excellent. In case of DC coupling, it requires the capacitors, right? It need capacitors. It will have a direct DC coupling. So as you can see, there are no capacitors present over here. The temperature stability is poor over here, and it's good because generally the devices are matched over in this case. And in case of outputs, it has only one option. It has two complementary outputs, so that's also an advantage. But on the downside, the power consumption, it's lower in case of single stage amplifier, but in case of DFAM, it's high because basically both the transistors are normally on. All right, and this is just a VTC, the input output characteristics, and a very important term, CMRR, which is differential gain upon common mode gain. So in this case for DFAM, in addition to there are two types of voltage gain. One is differential gain and one is common mode voltage gain. So in addition to the voltage gain, we also evaluate its CMRR in case of differential amplifier. So how good does differential amplifier depends upon how high the value of CMRR is. And to the advantage, it's also its input impedance is quite high. Okay. Anyone has any query over here? Okay. Then we come to the analog VLSI part. So from here we start with um, dealing with circuits which doesn't involve any resistors. So here we can analog VLSI circuits will begin from here. So it's very important to look at analog design octagon. So all parameters are related to each other in this outer octagon. The parameter noise is related to both power dissipation and linearity. Linearity is related to noise as well as gain. Supply voltage is related to voltage swing and gain. So in this case, if we consider this example, voltage swing versus power dissipation. So if you have a small voltage swing and the gain is 8, you have a full voltage swing available. But the MOSFET is on in both the cycles, so it will lead to high power dissipation. Whereas if you have a reduced voltage swing wherein the MOSFET is only working in the positive half cycle, then we can have a decrease in the power dissipation. So it's kind of a trade-off between the voltage swing and the power dissipation. Similar examples can be seen between the gain and our input output impedances. So if the input resistance is high, the gain decreases. And if the input output resistance is high, the gain increases. So also we can see about the linearity versus the speed. So whenever we have, normally the digital circuit requires a very high switching speed. All right. And whereas in case of amplifiers, we don't worry about the speed, we worry about the linearity. So this is an application where is used for the amplification, and this is used for your inverter application like digital circuits. Okay. Can I move on? Anyone, any query?
Yeah, we can move.
Okay. Then let's look at the MOSFET characteristics with a deeper meaning, because this will reveal a lot of details. So we all know about the output characteristics, drain characteristics of the MOSFET. So it's divided into different region of operation, the triode one and the saturation. In saturation, the MOSFET will behave as a constant current source. So in this case, it will behave as a constant current source. In the triode region, it's slightly linear at very low values of VDS, and we can determine the two resistance R on and RO. RO is associated with the operation of MOSFET in the saturation region, and R on is associated with the operation of MOSFET in the triode region. Their definitions are different and the values are also different. Usually RO is very, very high in kilo ohms and R on is quite less as compared to that. Then we reveal if we go for a very small value of VDS, the MOSFET is working in the deep triode region, and this is the condition for that. So in this case, we can determine the RO. In this case, we can see that the MOSFET is behaving linearly. So it can be used as if it is used as a resistor. Okay, so a simple MOSFET, the characteristic will reveal that it can be used as a constant current source like this over here. Here is the equation of current we all know about, including the channel and modulation. Okay, so channel and modulation is like in the saturation region, the current is only dependent upon, was independent upon VDS, but in this case, is slightly dependent upon. So in this case, ID is a function of VGS and VDS, strong function of VGS, but VDS is also involved. So that is the channel and modulation parameter. So here, if you can see, sorry, it's a function of VGS and VDS. Okay, so what important information do we get over here? Important information from the deep triad region is that your MOSFET can behave as a controlled resistor, electronically controlled resistor, and its resistance can be given as follows. It's 1 upon mu n Cox W by L VGS minus VTH. All right, where these parameters are like mobility, which depends upon the device, gate oxide capacitance, which depends upon the gate oxide thickness, aspect ratio, that is WNL, and the threshold voltage. So yeah, so the deeper meaning involved is that MOSFET, same MOSFET can behave differently in different operating regions. Okay, now about the MOSFET transconductance. So basically there are different formulas of MOSFET transconductance. As you can see, there is 1, 2, and 3 will all reveal the different nature of the characteristics. So basically transconductance converts an input voltage change into output current change. So in basic definition, it is GM is delta ID upon delta VGS at a constant VDS. So it's the MOSFET's amplifying power. So basically, the higher the GM, the more current swing you can get for a given voltage, gate voltage swing. So which directly set the voltage gain of the amplifier. So basically, what I'm saying is, if voltage gain depends upon, if let's say if we have a single stage amplifier, RS amplifier, then I mean the common source amplifier, then the voltage gain depends upon GM. And GM, if you have a higher value, then we have a higher voltage gain. So why does this analysis matter? Because in one case we are just keeping the aspect ratio constant, so GM is linear dependence upon VGS and VTH. So basically it's the gain and power trade-off. So since GM is proportional to square root of ID, doubling the GM requires 4 times the current. So the designers use this relationship to optimize the gain per watt. Sizing decisions. Now, GM is also proportional to WNL, right, at fixed ID. So increasing the transistor width will give you diminishing returns on GM, which is useful in layout area and performance trade-off. Now, bandwidth. For the bandwidth, the higher GM generally helps push the unity gain bandwidth higher. All right. And GM equations are the backbones in calculating the differential pair gain, current mirror matching, and small signal analysis. So in this case, in the first case, it's useful. In this case number 1, this is useful when you're designing a fixed bias point, and we want to see how GM scales with the sizing of the transistor or the overdrive voltage. Okay, so there's a linear relation to it. In case of second stage, this is used for current based design. So given the target value of ID, often it defines the power budget. It will tell you how GM scales with square root of ID or and with square root of WNL. So this relationship is most realistic useful in analog IC design, since ID is usually set by power constraint. So yeah, and the third one, it will give you the knowledge about that if you know the value of overdrive voltage and current, the GM is inversely proportional to the overdrive voltage. This is crucial because it reveals the fundamental trade-off between the lower overdrive voltage giving you higher GM per unit current. So it's basically GM ID efficiency. All right, so this MOSFET transconductance will give you about fundamental design trade-off, the the octagon which we talked about, it will give you the relationship between the different parameters to adjust for the design as per the design. Any query here? Okay. Hello, how much time do I have? Can I get to know? Do I have it?
Around 3:30, or you can take 10 minutes more than that.
Okay, fine. So we'll go a little faster because I have to cover some more topics. So why body effect matters in this case? Because in real IC, the body, so in the MOSFET, we have four terminals. So we have gate, drain, source, and the body. So if you analyze the circuit, the body is not always connected to the source, or in case of PMOS, it is connected to the drain, to the source actually, towards the power supply. So in a discrete transistor, we often assume that the source and the body are connected together. But in real integrated circuits, all NMOS transistors typically share a common substrate, while each transistor source may sit at a different potential. So that means the threshold voltage can change. So the threshold voltage without body effect, that is VSB equal to 0, will be this. But whenever the body effect is present, that is VSB is not equal to 0, we have this additional term. All right. So in terms of the hybrid pi model, there is an additional parameter which gets attached, which is GMB into VBS. All right. So if we don't estimate the value of, if we don't consider the body effect, then this estimation goes wrong and the threshold voltage calculation is wrong. And in case of your drain current is basically GM into VGS. It depends upon the output resistance. And this term, which is often ignored in discrete transistors, is also present, which is very, very vital and crucial information. It will tell you that why GMB is added as a second dependent current source. So this is what a circuit simulator computes additionally beyond the simple GM and RO, which when you use in the hand calculation. Okay. So what is the significance? The significance is that if we use a high level model, SPICE model, such as BISIM, then this GMB relation, that is GMB into eta times GM, where eta is usually around 0.1 to 0.3, is one of the parameter which is embedded in the SPICE MOSFET model when you run your DC analysis and your AC analysis. Okay. And the different capacitors, as you know, they are present to represent the parasitic capacitances. So these all represent parasitic capacitances which are inherently present in case of BJT. So it will help predict the frequency response or bandwidth depending upon the pole locations of these capacitors combined with RO and GM. Then we have Miller effect capacitances, because one capacitor is connecting input and output. So this is that capacitor. So we have to Millerize it. And then the transient response in switch circuits like sample and hold circuits will be also important. So what will go wrong if we don't consider this GMB or the substrate effect of body effect? So the simulation accuracy will be reduced. In case of we'll get wrong predictions, common mode voltage and CMRR predictions will be wrong, which we don't want it. All right.
There is one query from someone. Can you come
Yep.
again on body effect?
Okay. So in case of body effect, what happens is as I explained in terms of the symbol, without the body effect, usually the body terminal is tied to the source terminal. But let's say in case of let me explain it here. If we have a circuit which looks something like this, let's consider the simple circuit. So in this case, if both are NMOS transistors, let's say this body is connected over here and this body is connected to the ground. So in this case, let's say this is M1, this is M2. So in this case, my VSB is equal to 0. That means my body and the source potential are equal to 0. In this case, my VSB is not equal to 0 because this potential is not at the ground. So in this case, the threshold voltage in case of transistor 2 is just a normal threshold voltage. It will be evaluated using this expression. Whereas in case of M1, the threshold voltage, it's like we are underestimating its value, because its threshold voltage is not same as the threshold voltage given. We have additional parameters over here. So that is what the effect of body effect is. Oh, sorry. Let me go back quickly. Okay. So basically, in short, it will overestimate some parameters. It will it will undervalue some parameters. So the prediction of this simulations, if you don't include this GMB in the analysis, in the hand calculation, then your hand calculation and your simulation results will differ, and that difference is the body effect. I hope it is clear. I mean, you can reach out to me later. I can help you out in
Yeah, Dr. Shashi is saying thank you and got it, sir.
okay. Fine. And I'll just summarize the MOSFET models. So we have different types of MOSFET models. If we include, we are using ngSpice, right, in eSim. So we can represent, we can determine whenever we include a transistor, we can represent which a level 1 model or a level 2 model or a level 3, or we have a very high model, which is BISM model, which will include. So what this MOSFET model contains? It all contains parameters. So to represent a single MOSFET. So in level 1, we have VTO, gamma, phi, then we have TOX, all the capacitances, lambda, all right, along with the units. So they have their default values. So basically the SPICE is like simulation program with integrated circuit emphasis. So in case of level 1, it doesn't include subthreshold conduction or any short channel effects, and is usually for a level 1 model is usually considered to be very first hand model to use to check the circuit, but it's not very accurate at all. And next we have is level 2 model. It contains various higher order effects, but still it doesn't contain the short channel and narrow channel effects. So it suffers from large errors for long channels. And BISM tree, BISM tree model contains around 180 parameters of MOSFET. So we hardly know. Usually we come across at 5 or 10, but there are 180 parameters. Most of them are empirical parameters to simplify the equations. So the philosophy behind level 1 to 3 model was that to express the device behavior by means of equations that originated from physical operations. All right. So circuit simulation is important part of your any design process. So by simulating your circuits, you can detect errors early in the process and avoid costly and time consuming prototyping reworking. So that is very, very good for hand calculation and checking your design, or with the help of equations with the simulation software such as eSim or any open source software for that matter. Okay, now we quickly go through this single stage MOSFET amplifier. So the same single stage MOSFET amplifier can be called as a resistive load inverter or a MOSFET amplifier. So it has two domains. So this is my VTC curve. I'll quickly go to this. So this circuit can behave in a digital domain if it operates in region number 1 and region number A and B, and behaving in if it operates in region number C, it operates in the analog domain. Why? Because in region number A and B, the slope is 0. That means it's quite quick. The gain is 0. So basically, and in case of region C, is suitable for analog operation because the gain is very, very high. Okay, whereas in case of digital domain, we require just how fast the voltages changes between logic 0 and logic 1. So the same circuit can be used in terms of digital domain or the analog domain. Same is true with the CMOS inverter as well.
So there is one query
Yeah.
from Abdullah ji, like BSIM can be tested as practical model.
Yes, you can. Yes, it can be tested, but in order to test its accuracy, we should have that much equation and computational power. Since I told it's empirical parameters, a lot of empirical parameters are involved. So in order to get an accurate, it's the most accurate form of model. And before fabricating the MOSFET, we have the MOSFET parameters extracted from the foundry. So those parameters which are extracted, which will, if you want, if you import that those parameters in your model or in your MOSFET, then you, if you build that circuit, then will be a realistic circuit. Let's say if you're building a differential amplifier or oppositional amplifier, that will be a realistic values of transistors and realistic value of gain which you got. Okay.
Yeah, thank you.
Yeah. So like for example, in case of this, the power of the simulation tool is that we can verify exactly what is happening over here in this case. So in this case, I've simulated this and we got the exact characteristics. We have this noise margin levels. Noise margin levels are particularly useful concept in case of digital circuits. I think you have a digital circuit lecture already coming up. And in case of analog circuits, as I've told you, the gain will be suitable for analog amplification purpose when the circuit is operating in region number C. As you can see, the gain is not 1, it's less than 1, it's fine, it's inverting amplifier. It's around 8 over here in this region number C. Okay, sorry for that. Yeah. As I told you, we don't go for registers in case of integrated circuit design. So we have different types of common source amplifier with, so we have replaced the resistive load with the active device. So in this case, the active device is my MOSFET, the diode connected MOSFET. So three terminal MOSFET is forced to behave in the saturation region where it's behaving as a constant current source. So in this case, we have different diode connected circuits with its advantages and its disadvantages. So here is a quick comparison between resistive load, constant current load, triode load, and diode connected. As you can see, all the gains are non-linear, except in case of PMOS load or diode connected load, it's linear behavior. Static power dissipation is very should be low, and it's low. That's one of the also one of the reasons that we don't go for resistors in the integrated circuits. The power consumption is more. Also the size. So this is also the main culprit. So because of these two reasons, we don't consider resistors. The silicon area occupied by the resistors is very high. So in any amplifiers, in discrete amplifiers, we all use resistors, right, for biasing the transistor in the correct operating region. But in case of integrated circuit, we replace all the resistors. We bias the transistors with the help of current source, current mirroring, which we will discuss now. Then we have different applications of source follower. So let me quickly say that if you have a source follower connected to an antenna, the antenna and the CS amplifier output will not be having an impedance matching, because the output of CS amplifier doesn't have a very low output impedance. So what do? We use a source follower which will have a gain almost 1, but will have a low output resistance which will match with the antenna, and that will solve the problem of impedance matching. So these are the applications of source follower. And in other case, we can use common gate amplifier if we require for us to connect the amplifier to the input of the antenna. So in this case, the input impedance of the output impedance of the antenna is 50 ohms, and we can connect an amplifier which will have a low input resistance. So in this case, common gate amplifier is useful. So yes, source follower and common gate amplifier are also useful, but again, we don't use resistors. We just replace the resistors with the current sources or with a active device, active device as current sources. Yeah, that's the same thing, I guess. Then yeah, current mirror is extremely important. It's basically used to mirror the or copy the current from a current source with a constant current. It is technique to copy a current at different locations in a circuit. And this is a basic example of a current mirror. By the way, this I reference also is generated separately. So we have um, different way of generating this I reference current. We have uh, different designs such as supply independent biasing, temperature independent biasing circuits, which will generate the value of I reference. So we have a separate circuit to have a temperature dependent, independent biasing, or supply independent biasing to generate this. And here we can quickly see that in the relation is like I copy is W2 upon W1 into I reference, the simplified form. So this concept shows that we can just by uh, matching the transistors width, we can change the width of the transistor. Let's say I copy, we want it 5 times I reference, so we can change W to W1 accordingly. Yeah. Another good practice is that if you want to design, if you want to enhance the current mirroring, let's say by 8, the current factor by 8, so what do we do here is we don't just increase the width of the transistor, because let's say if you want I out to be 8 times I reference, so in this case if you just increase the width, let's say um, 8W upon L. So let's say in case of if you are making the layout, there will be certain, the length and the width of the layout, when we check it, it's not consistent, so there will be an error in this case. So what we do is, instead of doing this, we get we use unit cell design. So instead of doing this, we do this. So we have 8 transistors, each of them carrying around 10 microamperes of current, and that will add up to 80 microamperes. So this is like a design fabrication thing which we adopt. And the application of current mirror will involve current buffering, biasing the currents through the current biasing, and digital to analog converters. Okay, so these are few of the current mirror circuits. We have high swing cascode current mirror, then we have low voltage high swing cascode current mirror, which you can try it out. And we have seen discrete differential amplifier. Now we are seeing differential amplifier with active loads. As you can see over here, the resistors are replaced with the diode connected load, in this case PMOS load. And as we can clearly notice that the gain is not dependent upon any of the resistors. Those are the internal output resistance. And this circuit is also very useful, that is telescopic cascoding, cascode differential amplifier. It's basically to provide a very high voltage gain. All right. Then this is also a very important concept, that is a Gilbert cell. It's for in case of analog circuit simulation. So it's an analog voltage multiplier. And why it is important is because it's used in RF mixers. Oh, sorry. It's used because of its feature of automatic gain control, AGC, and it's basically used as a analog multiplier. So it's a voltage control variable gain amplifier. And as you can see, it's all consisting of all MOSFETs. These resistors also can be later replaced with the transistors. So yeah, a Gilbert cell also, I think in one of the earlier marathons, people have simulated, students have simulated Gilbert cell simulation also. Then we have, I have 5 minutes more, or can I conclude now?
You can take.
Okay, so this is also a very important concept of OTA, that is operational trans conductance amplifier. So it's different than op-amp. In case of op-amp, the input is voltage, the output is voltage. In case of OTA, the input is voltage, but the output is current. So that's the primary difference. And in case of op-amp, V out is AV times V in minus V in 2. As you can see, in case of OTA, that is operational transconductance amplifier, I out is GM times V in 1 into V in 2. So yeah, design of OTA, it's similar to op-amp, but it's one of the stages of op-amp. It's not a complete op-amp. So it's a voltage control current source. It converts the input voltage to output current. And op-amp can directly drive a speaker, a LED, or a register, staying at the voltage you command. Whereas in OTA, it relies on the current source, how much current to push. So if you ask it to drive a low impedance load directly without proper loading or conversion, the output won't behave ideally. So basically, it's a current output device. It's a voltage controlled current source. and it's basically it's input differential amplifier, what eventually becomes a full op amp once you add more stages. So it's a good analog circuit to analyze and design. As you can see, it can be a part of a differential amplifier, as you can see over here in this case. Oh, sorry. And it doesn't contain any resistors for that matter. Then we can have a folded cascade op amp. So it will have a very wide input common range, and it has a slightly lower bandwidth, but your AV is very, very high. But the disadvantage is that it's a single-ended output, unlike op amp, which will have a dual output. And it actually signifies the interconversion. So in the first stage, the voltage is getting converted into current. In the second stage, current is getting enhanced into different value. And in third stage, the current is again back converting into voltage. So yeah, the input is a voltage and output is a voltage. That's an example of an op amp. Okay.
So there is
Um,
one query
yeah.
from Abdullah ji, that if the middle circuit be used as a OTA in the previous slide,
This one or
they
this
didn't
one?
mention. Maybe we'll wait for
Which?
the reply.
Okay.
Like 1 minute before. Ah, yes. He's saying yes. This middle one.
This one?
Yes,
Sorry, I
yes,
didn't
yes,
get the.
yes, yes, yes. That
Yeah, yeah, yes, yes. It can be used. It's a single-ended differential amplifier, we can say. It's just converting voltage into single-ended output. So yeah, we can.
okay.
And then coming to the application point, this is I think my last slide. Yeah. So we can have a two-stage OTA, which is a very famous analog circuit. So I have differentiated in terms of biasing. So we bias it with I reference. Now there is a separate circuit to generate I reference also. I've already talked about it. So M8 and I reference are used for biasing. Then this is my first stage, which is my single stage OTA. This is my OTA only. And this is my second stage, which will provide some of the gain. So its important parameters are the voltage gain, output voltage swing, and if I compactly represent, it will, now this circuit will have some problem that its output resistance over here is not fixed. So to compensate that, we have a Miller compensation capacitor, which is complete, which will complete the divine. Basically, it will make the OTA gain more stable in versus frequency. So these circuits are designed for gain to be greater than 5,000 or more, and provided the following parameters are given to us. I mean the requirements. Okay, let's see an example. So in this case, this is the design circuit. I am sorry, I couldn't explain in more details about it, but these are the specifications given to us. Within these specifications, we have to design the circuit and simulate. So basically, the V out max was supposed to be 2 point, within 2 point, I think, yeah, within plus or minus 2, it's 2.3. That's very good. And power dissipation should be around 2 milliwatt. Here it's around less than 2 milliwatts, I suppose. And the voltage gain was supposed to be greater than 5,000. It's giving around 7,732. Whereas if I simulate this device in an open source tool, I'm getting a current of around 5,145. As you can see, there is a difference of, let's say, when we calculate over here 7,732 and 5,145 because of the level of models used over here. I have used over here level 1 models, which will hardly take any parameters. So if you use a higher BISM 3 model or a similar model, we can get quite accurate values of these two simulation results. But yeah, um, uh, this is what I have to say for today. So yeah, thank you for your kind attention. I can take questions if you have any.
Hello, sir. Good afternoon.
Hello.
Good afternoon. Can this
Good afternoon.
level 1 and VSIM with models, can we prepare a paper and make a comparative study of power and timing kind of thing?
Yes, yes, we can. In fact, many of the researchers do that. I mean, nowadays, what they do is from the foundry, they extract the model. Let's say 180 nanometer, we are building a 180 nanometer transistor, which they actually fabricate. They extract the model parameters from it and they import in the SPICE simulator circuit to get the realistic, like you said about timing parameter analysis. So we can do all the analysis. So it's basically start with one transistor and we can reflect this to all the transistors used in the circuits. So yes, to your answer to your question, yes. I also apologize that I couldn't give you some examples of the eSIM circuits which I've simulated before. I mean, it was there in my laptop in back in India, but currently I don't have any access to that. So that's why I couldn't attach those circuits. But I've used open source tools to show you all these pictures.
Yeah, it was very nice session, and it was actually like bridging the gap between academic, what we can say, the way we learned at the class and the way we are now simulating it. So you definitely bridge that gap, and we are very lucky to have you here. And as I
Thank you.
see, most of the comments are they are very grateful for the session, and also they are asking for the PPT that the way you wrote here, all of the things were so nice. So they want the final compiled version of this PPT or
Yeah, yeah,
PDF.
I can give it to you annotated and without that also. I will share it very easily. I've also shared
Yeah,
my links over here. You can go through them. GitHub link actually it's containing the projects which I've involved in with Fossey, and this YouTube channel contains all the lecture videos which some of it I have used for the today's topic. Sorry, I didn't get much time to prepare. I don't know how I did. So
no, it was a great.
whatever I could accumulate in 1 hour session because it was very limited time and analog circuit simulation is a huge topic. It's we can have a complete different FDP for it. Still, it's not enough. So yeah, but still I could touch the surface. So in analog circuit simulation, it's all involving how well you can describe the circuit well, how accurately you can write the model and move it more and more parameters. So that will give you the more realistic feel of the actual what the circuits are doing.
Yeah,
Yeah, I'll definitely share the presentation slides with you. So can I unshare my screen now?
yeah, yeah.
Okay, unshare my screen. Where is the? Okay, yeah. Okay. So thank you for having me.
Someone raised the
And
hand. Someone
okay,
has raised the hand. We'll see.
you all have a query?
Someone has a query. No, now they again put their hand down.
Okay, fine.
Yeah,
In case of any query, you can reach out to me. I'll share my email ID to Varad and he can convey that. I can include that in my slides and you can always reach out to me for any query.
yeah,
Okay. So can I take my leave, Varad?
yeah. Thank you so much again to being here at the Faculty Development Program 2026. Yeah, we are sharing the attendance. So for now, as our analog circuit simulation lecture has done, so we will be having one small hands-on for now, and then we will be connecting with everyone at the evening session at 7:30 to 8:30, which will be on topic digital circuit simulation using eSim and McCarthy, which will be taken by Steve Hoover, who is our one of the industry partner and who is also a founder of Redwood EDA from USA and who is former logic design lead at Intel. So yeah, we'll be sharing attendance. Timing is at 7:30 to 8:30. It is as per the schedule shared to everyone. Deepak sir, recording is still on, na?
Yes, yes.
Okay. We'll wait for 5 minutes to everyone get rejoined. Due to one technical issue, our link got uh, deactivated. But we are still on. We will wait for 5 minutes and then we'll start. Yeah, we will having it. Yeah, so we'll start. So for now, it is two sessions are there. Like the one is evening session at 7:30 to 8:30, as I mentioned. And before going to that, that is a digital circuit simulation session. So it is always best practice to before going to a digital thing, we will first see uh, to get our first digital signal. So I hope everyone are still here. The attendance will be shared again. The one who already given the attendance, that is fine. Yeah. Uh, our team has floated attendance again. I will just copy and pin it. Okay. So now I will keep my camera off just due to the network to make it smooth. And okay, let's move to my PPT. So As we discussed today from the Professor Indrajit sir, that it was all about analog. And after the analog, like in analog also, we discuss about diodes, amplifiers, BGT, and many more. So now thing comes like, what about digital? And if it's something related to digital, we need to have a digital signal. So as everyone know, digital is zero and ones, like a pulse setting. But now we will take one example for a hands-on, and what I will do, I will make it very quick so that we will conclude the session quicker, so that this time we will save and we'll continue in the evening with the digital circuit. And after today, like tomorrow, we will again have a wider time slot, so that in case something is remains, we will be sharing. So let's talk on the topic of flat top sampling, which is nothing but a practical signal acquisition model, where the everyone has know the sample is the process to convert analog signal to a discrete signal. So to doing that, so it is like, why flat top sampling? Just because it is very much closely mimic the real world hardware, and also provides excellent noise immunity rather than the natural sampling. Then how it does that to make the top amplitude constant? So yeah. So ongoing to the direct hands-on, as in the morning half we discussed about half-wave rectifier, that was like completely on the eSIM tool. So now the same thing we will do with the eSIM software, but now the library will be different. So how library will different? Library will be on that eSIM underscore only, but there are few more components to be needed for this model. So which are those? The first sign we already discussed. Second is DC, that is a new model, that is for the DC source. A constant voltage will be given from this source. Third one is resistor, that we already seen. Then there is a capacitor. For capacitor, we'll search for eSIM underscore C. The transistor. In eSIM, we need to search eSIM underscore PNP, NPM, and there are two more that we can use in. For amplifier, we have one general purpose amplifier LM741, which is available in eSIM underscore subcircuit library. And we will obviously use ground and plot vision. So from the morning session, I hope everyone is much having a much clear uh, understanding of eSIM tool, how the flow is and all. So now we'll quickly jump to the circuit. So everyone can take a screenshot of this, that is fine. And there are two transistors being used. The first one is PNP and the other is NPN, if the image is little blurred. So for that I mentioned that the first is PNP, although there is written also in the vertical way. The capacitance, register values, and DC that I wrote, just in case the picture quality or the internet connection is low. Yeah. So after the Indrajit lecture, it was all about analog. So we will take this thing forward to get our first discrete signal. That is like a first foundational stage to work on the digital domain. So let's do that. For that, I will pillar, and I hope everyone is aware of it, that I will just quickly recap. First was the creation of the schematic like this. After the creation of schematic, we used to annotate that. After the annotation, we used to create a netlist and specific to the spice netlist. After the spice netlist, we used to have this king. King means KiCad to ngSpice converter. When the netlist is imported, exported, that netlist we will use to assign the parameters, the values to the circuit. After this king, we have parameters that in that king only we'll add these all parameters and we'll convert that. Once we converted, see, last time what we did parameters uh, up to device modeling. But now we have one sub-circuit here. So sub-circuit is which one? The LM741 is a sub-circuit. Why it is a sub-circuit? Just because we have created this model using a transistor level, TTL level, and now we make that TTL circuitry as a internal circuitry, and we design one symbol for that. And whenever we want to use it again, we are importing that symbol of LM741, that is a general purpose operational amplifier. We are taking it, and in the back end we need to link it. So how will we link it? We will add a library like this. So last time we did analysis, source details, ngSpice model we didn't, but device modeling we did, sub-circuit we didn't did, but now we will do that. And after the sub-circuit addition, we will click on simulate, and once we simulate, the ngSpice plot should look like this. This is the waveform, this is the frequency, and you can see the top are flat enough. So here we can say that this is a flat top sampling example. Although there are two more, like one is the ideal sampling that we used to say impulse sampling, and the practical sampling. Just because taking a flat term sampling here, and what I will do, I will give the natural sampling as a mm, like as an example that participant can do in their free time, or if they did it successfully, they can share with us. And yeah, so this is the Python plotting for the same that we discussed in morning. I will show you in that hands-on only. For in the PPT aspect, we can actually as the ngSpice plots, we used to if we want to modify anything in ngSpice plot, what we do, we used to write something on the ngSpice terminal, and then only things appear. But in the Python plot, if you want to make any changes, like say change the color of that waveform, then these options are there here itself. This is the ngSpice plot, and you can see this is the adjust icon. So once we click here, we'll get a different option to adjust the figures, to configure the waveforms, and many more. So now what we will do uh, before concluding, this is some assignment in the sense if someone wants to test some more example. So this is for the natural sampling. But before going here, I will quickly show my eSIM. I hope my voice is clear enough. And I'm audible to everyone.
Yeah, it's clear.
Okay. So I will quickly show you. So this is the eSIM again. We are back to eSIM. As now we will be taking one little good example that is a flat top sampling. So one that is here itself that I already prepared, that I will just open and show you once, so everyone can see. This is the design, which has two op amps. One is this LM741 and other is same, having the three resistors. One is here of 10 kilo ohm, other is here 10 kilo ohm, and one is here of 1 kilo ohm. Also there are two DC source, one of 15 volt and other is also 15 volts, and there is one pulse used and one sine. So this circuit I will redesign in front of everyone so that everyone get to know how exactly or which components are needed to get these things done. So I will just close this, and if you want to see the output, we can have it here. So this is the frequency. Again, as I say, if we want to zoom it, then we can right click on our mouse. And if we drag like this, and if we leave that mouse button, then it will zoom. In this way, we can zoom as much we want. And particularly, I will close it here. This is V in. And for the Python plotting, it is mentioned as here. So we'll just take F in, out, and frequency. We'll go down and plot. So I can see there is a frequency, the sine wave is there, and that is now tracked by this output. So let's do it now. So to doing a hands-on, what we will do, we will create a project. Let's call that project as a flat top test. I will just click OK. Now this circuit is here. Whomever is trying to do the hands-on with me parallelly, or maybe after the session, they can follow my instructions step by step so that they won't get any issue. Even the session is recorded, in case someone wants to do it in their leisure time, they can do. So for that, uh, I will go step by step. I will take only 10 to 15 minutes to do it, and then we will conclude today's session. So this is a flat top test example project that I created here. And now what I will do, I will click on the schematic option. It will create a schematic file within the project. Now it is asking me whether you want to create a new schematic. I will click yes. So as I shared PPT with everyone can look into the library, which library is needed for this circuit. So for that, firstly, we will click on add symbol option. As I mentioned, the library is much wide. For now, it is loaded, and now I will take the components one by one. The most important component here is LM741, and make sure that it is under eSim underscore subcircuit. Just because we already spoke, component under eSim subcircuit are the component which has the spice model linked in the backend and can be used for the simulation. Those which are not under the eSim underscore library, all those are intentionally used for the PCB design as they have footprints to be used. So I will take it, I will press OK. In this big canvas, I will place it here, and I will also press Ctrl C to copy. And I will press Ctrl V to paste. So now I have two op-amp here. What I will do, I will add the other component. So next important component is transistor. Here we'll require two transistors, and both transistors we need to search like this. One is eSIM underscore PNP. You can see it is under eSIM underscore devices, and I will click OK. So now I have PNP transistor. To rotate that, I will press R. It is now rotated. I will place it somewhere here. I need one more transistor, but it should be NPN. So I will search eSIM underscore NPN, and I will press enter. So again, I need to rotate it. I will press R. So to zoom in and zoom out to the canvas, we'll use mouse scroll option only. Now I will place it here. Now I need a resistors. I will press A again to search for eSIM underscore R. Hit enter. I will place one resistor here. I will press Ctrl C to copy, and I will use Ctrl V to paste. And I will press R to rotate. I will place one resistor here. Again, I will press Ctrl V, and I will place the resistor somewhere here. So now what I will do, what is left? We left with the source. So we will use DC source. For that, I need to press D and C. There are one current source, DC current source, one is DC voltage source. I will use voltage source here, capital DC. I will hit OK. Now I will place it here, somewhere here. Will copy it, and I will keep one here. Now The sine wave, we need a sine, so I will search sine and then I will click OK. I will keep it somewhere here. I need a pulse, so I will search PULSE. Whatever I'm searching, I have taken a screenshot of it with the library and I have attached in the PPT. At the time of the hands-on, if someone is doing parallel to me, they can also see that and perform the same. I kept pulse here. Now the remaining things are plot and the global level. Before that, I will wire everything. So to wire, I will zoom the part. I will press escape function first to remove this add symbol option. So I press escape. It makes my cursor again normal. Whenever I go to some point like this, it will give me option to wire. Otherwise, you can press W. It will start the wire wherever your cursor is, and I will join it. Similarly, I will join this part, and now this one I will join like this. For the op-amp, I will take a feedback like this. Here also. Okay. Now I will join the transistor with this. So this is now I'm just doing a wiring. So either you can follow me or you can take a direct reference from the picture that I shared. One component that we missed is capacitor. We'll take eSim underscore C capacitor. We will add it before this resistor and I will press W to attach it here. So now this one, this is the sign. I will make the connection like this. So sometimes when we cross these components at the terminal of that component, that time only it get shorted or it add a junction. So whenever it happen like this, now if I am placing a wire above this wire, it is not creating a junction. But why here it is created? Just because this component, wherever it ends, this point if we intersect, then only added junction. So for now, if it is still added junction here, then it will not work. So what I will do, I delete the related the junction. So now you can see it is intersecting, but as long as there is no junction, it is not internally connected. So if you still wanted to move the wires, there are two ways. One is to move. When we move the wire directly, it disconnect the wire like this. So for now, we don't want to disconnect. We just want to move it. So I will press G on the keyboard so that it will just help me to move it rather than disconnecting and move it. Again, I will press G here and again here. If I press G on this component and if I move, then you can see the wire is not disconnecting. So this is a very nice feature to not to disconnect a wire and we can directly move it. This is left. While performing this, you can directly take a reference from the picture from the slide and you can do the same wiring. Here one ground is missing. I will add eSim underscore ground. I will add it here. This again press W to get it attached here. I kept an empty wire here just because I want to add a plot and the global label, as this is my input side, and same for the output side. This is the output stage. So what I will do, I will keep one open wire here and one open end here to add a global label and the plot. Now this transistor is left with connection. So this one I need to attach somewhere here. So as long as this is also again going inside from here. So what I will do, I will keep it here for a second. Again use G. If I use M, what it do, it disconnect the resistor from that line, and it takes so much time for a user to rearrange the wire. So the good feature is to use G, press G, so that this resistor will stay connected and you can move it little down. Now I can again wire that resistor from here. So this is done. We are we are almost done. This upper part is yet to connect. So this one we will connect at this source, and this one to here. So if we did this in some workshop, most of the participants forgot to put the unconnected flags here. To do that, on the right side, here is a add a no connection flag queue that we studied in the morning half. I will click it here and I will add the no connection flag on top of this and top of this. So now almost everything is done. Only plot are remaining. So I will click A. I will search for plot V1. I will press enter. So for now we need a three plots. I will click one here. I will copy, uh, and I need one somewhere here. So I'll keep it here. And one plot I need at the output stage here. And the global label, you can see on the right side, this A is for global label. Here I will be adding OUT for output. You can use any shape, but it is anytime nice to depict the same thing that we are doing as it is output. So I took output shape. It will work same, but it's on you. Here it is a frequency. I will type Fs. I will just say okay. To rotate, I will press R. Now I will join it. And now this one I need to add here at the like this is connected. You can see whenever someone wants to see whether my wiring is connected or not, they simply press G on the junction G, so that they can see whether it is connected. As I see, when I drag it somewhere, it shows it is connected. So as long as it is connected, it is fine. Right. Now, almost this one, this input side, we need to do it, and we need to add a IN as the input stage. I will rotate. This is a very nice example to do in a hands-on, and I hope everyone will do. If they are parallelly doing it, then please let me know in the comment section that you are getting outputs. So now about values. So as I said, the capacitance value is 0.1 mu. The resistor value, as already mentioned in the PPT, 10 kilo ohm. This capacitance same 10 kilo ohm. To add the values to capacitor or any component, what I am doing, most of the time, this is R question mark. to just say this is the register 1, register 2, register 3. After the annotation, the question mark will go, but the esim underscore r, we need to double click and we need to say how much resistance we want. For me, it was 1K, or you can press V on keyboard, it will pop up same thing, or you can double click on the component and it will give the symbol properties. Here, value, under value, you need to write a value. Anything will work, but I'm just showing all of the way to do. Here it is by default is no flag, so no need to connect anything. Now capacitor is done, resistance is done. For pulse, as I said before in the morning, the pulse, the sine, all of these are the sources. So either you can give the values to the sources in the schematic, but it is always better to give the values at the post stage when we take the netlist and then we do simulation. That will be very easy and convenient when we want to change some parameters. If you want to change the input, why? Sometimes we are working on voltage regulators or amplifiers or anything where we wanted to change the input. If it is a example of some voltage regulator LM342, then it is a like a variable voltage regulator. So it's, if you want to see whether it is actually performing well, so you can in the console, that in the dock area you can give multiple voltage and simulate it. It will be very easy to simulate. Otherwise, if you want to make any changes in the schematic, you need to save, annotate, and then convert the netlist, then do a KiCad. It takes some time. So it is ideally we should give the values later. And if you are sure that I don't want to change the pulse value at all uh, after my design, then you can give the values from here only. To do that, just double click on it here, and this is the value of pulse. So, as per the conventional method of having putting the pulse value, you can just add it like a zero, then space, then amplitude, then space, then damping factor by the conventional method, like a duty ratio, this, that, everything. To give the value of DC, you can see DC here. I will double click here and I will press 15. Same with here, I will show double click here, and for just a reference I'm adding value here. Both do same thing. R1 is just for the reference, so no need to worry about that. Now I can see almost everything is done. This area is done, this area is also done. Transistor is connected, capacitance is before register, amplifier is there, and yes. So now what I will do, I will save it. I press Ctrl S, I go to File, Export, Netlist, Spice Netlist, and I will export it. So I click on Export, and by default the location will be there. So I will just press Save, and then it will ask for annotation. I will click on Annotate by default. So again, you can see there is a one star. It means file is not saved just because we annotated it now. So I press Ctrl S and you can see the star is gone. Now I will minimize it, and don't worry for the previous circuit. We can either close or keep it like that. The important thing is in this console, we should see that flat top test is selected. So for that, you can either double click on it and press on KiCad to ngSpice. Now we got the option to edit what type of analysis we are doing. So for here, we'll start with a 0 millisecond. To do it, click here, 0 millisecond. Then I will take a step of 0.1 millisecond. And as it is a sampling and frequency, this sampling frequency, this, that. So if I take it for a very long time, I will get a unnecessary, very big raw data. So I don't want that. So that's why I took a very small scale. For that small time, I am just running it. And for the pulse source, there is two source. One is pulse and one is sine. For pulse source, I will start it from -5. Then the pulse value I will keep at 5. I won't keep any delay. The rise time, let's take it as a 0.001 m. I will copy it. I will keep the same for the fall time, and for the duty ratio, we will keep it like this. And now for the sign, I will keep it like normal, like offset 0. Let's do amplitude of 1 volt. Let's uh, let's keep the frequency of 250, and no need of delay. If you want, you can do. We can play around it. Nothing to worry. But for now, keeping like this. ngSpice model, no ngSpice model is here. For device modeling, now we have two options. In the morning, we only have one, that was diode. Here I will add transistor. So you can see there is a list. So in that list there is a transistor. I will double click on it. Before click on any transistor, just make sure which one it is. It is NPN. So we will look for the NPN transistor. Although we have some other transistor if you are looking for, and you can even design your own. That I will talk about tomorrow. How to design your own transistor. As Indrajit sir discussed in this today's session that there are many things that we can model. So again here transistor and then PNP. This is PNP, this is PNP, this is NPN, this is NPN. Now important step, that subcircuit should be added. One is LM741, other is same. So I will click add. See, this time subcircuit is present in the FOSSEE folder, in the eSIM folder, within the library folder and subcircuit library. It will automatically redirect you to here. You can either type here LM, and you can see the list of different ICs or subcircuits. You can see the first LM741. I can click here once, and the name is here. I will click select folder. Or what you can do, you can manually locate it. Like you can scroll down like this, and then you will find it. I can find it here, LM741. Then I will double click here. This one, the rescue backup is no longer needed. So in case somewhere you found the rescue backup, you can delete it directly. So again, I will scroll it. LM where it is. Okay, I just modified it so I can see it here. LM741. I selected it. So both are selected, both are same only. And then I will click on convert. Then I will press OK. So now I will simulate it with this third button. It will ask me for ngSpice plot or not. So I will say yes. Now I will wait for the simulation to happen. And as you can see, the one that I got is V in, one is VFS, and one is V out. The agenda of this today's hands-on was to see whether this sampling is possible and how it is doing. It is doing good. It is as per expected. And if you want to zoom it, you press right mouse key and make a marker like this and release it. So it will zoom. And here also you can say that is a flat top. As we use two op-amp here, if we use one op-amp and then we can get a natural sampling that I kept in that PPT only at the end for a try. If in case you found any difficulty to perform that thing, then please let me know. My emails are still attached, and you can anyways contact via email to contact-esim@fossee.in. So for the nodes, the frequency in, out, and one more thing. Now you can see this canvas is not looking good. Good in the sense there is some blank space. So I will first plot and still it is not like this. So I will click on the zoom to rectangle we can use, or we can click here. So this is just to make the border width small. So you can see I'm just scrolling it. So now it is coming up. You can directly manually type point 0.1, point 0.7 or point 0.8 to make it as good you want. So I'm just adjusting it some way that it looks better to see. So I think this is okay. We'll close it. If I don't want the frequency, I will close this. Then also, this is the expected waveform that we want. And for the RMS or the multimeter reading, I will click here and we will get the multimeter readings for the both nodes. So in this way, what I am trying to say, the flat top example that I shown, it was from scratch, so that if anyone is using eSim version 2.5, if they followed the steps that I shared today by following the YouTube video, it will 100% will work. And in case of backup, this flat top example I already uh, zipped and shared in the drive that I shared in the morning. I will still attach it here. This is the both things for the day, for the reference of the day 2. Pulse timing. Yeah. So pulse timing and everything is attached in the PPT. I will show you it again. And the YouTube link. Yeah, I will let me add the YouTube link as well. For daily YouTube link, we have one common YouTube link called uh, I just added in this comment section. One is live link. Whenever there is a live, you can click the first link. And for the day 1, I have attached the link, and for day 2 also I have attached. Even though if you want to see all of the YouTube live streams, you can directly click on this option. Second, please explain how to plot DC characteristics of transistor. Yeah. So yeah, tomorrow we will be seeing that only, other different characteristics, and with this one more example. Just because like for today's session we will make it concise, just because we are having a evening session. If we make this session little longer, then it will be I think it will be hard for the all participants to stay tuned at the evening. So yeah, definitely I will take care of that thing. Please explain how to plot this. Yeah, I will be showing that only. Provide YouTube link is done. Pulse timing also added in that PPT. Okay, let me show you the drive. So this is the drive that is there. One I kept as a hands-on PPT, PDF format of the PPT, and one is due to the network issue, it got me disconnected. Yeah, let me just check once. So I hope at least everyone got to know. Is any participant was following me at the time of the hands-on? Yes, okay. Dr. Shashikant. Yes, sir. Yeah, okay. Yeah, thank you so much for following. So Basically, this example is also very doable. Like if you just follow the steps as I said. And one thing like yesterday we install eSIM with the halfway rectifier that also work. And if this today's session, I will just share my screen again. Okay, I will hide it. So in this FDP presentation, first thing in the morning we did with the halfway rectifier. Now we did with the flat top sampling. Still that project file is available in the drive. What I'm requesting to all of the participants to give a try to this natural sampling. Okay, this is a natural sampling example. You can use the same thing like same values also. Almost everything is here, and you can just take a reference from here. You can take a screenshot of this, and in case someone face any issues of this, then we will be uh, I will be showing this thing how this will also work, and the expected outcome from this will be a curve waveform like a natural one. Like as of now, the due to the amplitude is flattened, like it is keeping the amplitude constant throughout that pulse, so it is flat. So for that particular example, this one, what it will do, it will keep the natural waveform like this, like a curve. So that is the expected outcome. If someone is doing this also, please let me know by tomorrow. Like tomorrow in the session only, I will ask like if someone has followed, and I hope like it is very much doable. And if possible, I will add some more slides here only in the meantime to give some hints to perform it. So the my one questions to all participants is natural sampling example is not there in the PPT. Yeah, natural sampling example is this one. Let me show you. This is at the end. This one. This is a natural sampling example. This is I'm just providing it here without uh, any what is this parameter, just to participant to work on it directly. If they fails tomorrow anyways I will be showing this also. So and it is also very easy to do. You can use the same parameters, almost same parameters to perform. Just otherwise you can just remove one op-amp from this area, and then you can just what we can say remove the unnecessary part and then join it. So it is will look similar to it and it will work. Let's go back to the session. PPT. Okay. Yeah. So I hope I just want to ask everyone that do everyone is clear with the flow at least. The flow is just three steps. One is simulation, kicker to ngSpice, and the simulation. Other than these three, what we have lot much capabilities of eSIM in terms of digital domain, in terms of mixed signal domain, in terms of model design. We will design our own diode, and it has a very wide range of capabilities that we will be discussing in the coming session. Just the these early sessions are meant to be uh, design a way that everyone get an understanding of the eSIM, how it looks, where are the functions. Now everyone know where are the functions, how are the functions. Now we can directly use those functions to deal with our topics. So yeah, I hope everyone uh, got everything. Or if still have any doubts, they can feel free to ask.
Overall,
Hello.
hello.
Yeah. Yes.
Yeah. Well, actually, I'm facing difficulty in plotting these characteristics. I haven't find any option to plot the characteristics, device characteristics,
Okay.
IB characteristics. Transient and frequency response I am able to plot, but characteristics was I am not getting.
Okay. So for
DC
I.
characteristics.
Hmm, hmm, hmm. So for IV characteristics, what we need to do, as of now, we done voltage versus time. So to do
Yes.
current versus voltage, we need to add one more plot called, let me show it here in the schematic only. So as long as we know this is the voltage plot, which is taking that node voltage. If we click again A, and if we search for plot underscore V2, this is a current plot. So if we take a current plot and voltage plot, we will get two voltages, like a two waveforms. And here is the ngSpice plot. So here what will we do? We will type plot V in and V out. So in this case, like this has to be designed it again. So
No, no.
for like
Actually, I have a request that you just do one thing. Just you plot one IV characteristics for a diode, normal diode. Then I will get. For other devices, I will plot. Like for BJT, for MOSFET, I will do. But just you just show me IV characteristics for a diode.
okay,
Is
okay,
it
okay.
possible?
Is it okay if I just do it by tomorrow?
Yeah, no
Because
issue,
like
no issue.
it is fine.
Yeah, because in the
Because
example also I have
yeah.
searched, but I didn't find this IV characteristics. In same problem I have faced in HS Spice also.
Okay, okay, yeah. So what I will do, I will be discuss DC, AC, and the IV characteristics, everything by tomorrow. So that will help everyone to get things aligned. So maybe most of them have the same things. Yeah. Hello.
Sure, sure, sure. Thank you.
Yeah. Yeah. Just because
Tomorrow,
like
your
yeah.
session will start in afternoon.
Let me check the schedule once. Yeah, it is around like tomorrow in the morning half. We have one session up to 10:30 to 12, and then we have a session 12 to 1. So in this 12 to 1, my colleague will be showing some example, and we will be like together coordinate with each other, and we'll keep this session also there
Okay.
around 12 to 1 itself. Yeah.
Okay.
Yeah. So in this
Thank
way, what I can do this like two more doubts was there. So these two and this IV graph and one more thing I will take at the same time.
you.
So that like before half the lot many participants joined, but just after the Indrajit sir lecture, the meeting was ended for everyone. So like most of them has maybe left. So what we can do, we will summarize everything tomorrow also. So it will be help everyone. Yeah. So I hope everyone is still here and everyone has done with the attendance. For today, the attendance of afternoon has done, morning also done. So evening, I just request all of the participants, dear faculty partners, faculty members, researchers, students, to kindly attend the evening session. That is really nice from the Steve Hoover, who is our, one of the industry partner from Redwood EDA. Uh, like they are the founder of Redwood EDA from USA, and they are the former logic design lead at Intel. So that will be very nice an interactive session from them. So I just kindly request all of you to be there, and yeah, we'll be meeting soon. And thank you everyone for the joining this session. Yeah,
Thank you, sir.
yeah, thank you so much.